Hello.
Sir, good morning.
Good morning. Good morning.
Morning,
Good
Mr.
morning.
Prasad.
Good morning. Good morning, Bharati. Good morning.
Hello, Nanda Prasad. Sorry, I had a mistake. I was trying to call that Hema Jawahar Reddy. Sorry. Okay. Uh,
Are we waiting for more participants to join? Hello? Hello?
I don't know. There is nobody from the host side, I think. You know,
Nobody from the host side.
coordinated. Yeah. I don't know.
Yeah,
There are,
Nataraj.
there are about 118 participants there. I don't know.
Ah. Okay. It was Nataraj on the line. Therefore, he says another 5 minutes.
Okay. Mhm.
What should I say there?
Okay. I mean, they keep telling that they should join
Good
10
morning
minutes in
to
advance and all
everyone.
that, but
I know.
Welcome to the day 2, the orientation program. So today the session, just I will hand over to HRS Prasad. Sir, HRS Prasad, you can take over the session.
All right. Okay. So, am I audible?
Yes, sir.
Yeah, okay. So, good morning to all of you and welcome to this day 2 of this orientation course. Intended for the internship or foundation course. Today we will be discussing about the avionic systems and the electrical system. The main focus is on the development that have taken place in the avionics and how it has helped either the pilot or the passengers, what way they have impacted the aircraft design as such. This is the total focus of today's discussion. And during the course of today, we'll be discussing the impact of evolution in electronics, evolution itself in the avionics system, the communication system, the navigation, landing aids, the cockpit instruments and display system, the recording systems, and aircraft safety and warning systems. Go to the next slide. When we say avionics, actually what we mean is the electronics that is used in the aerospace. In our case, the electronics that is used in the aircraft. In the aircraft systems, what way the electronics is used, how they have impacted the development and usage of the different systems on board. What you're seeing on the screen is the impact of the electronics in day-to-day life. You're all familiar with this, how the tremendous evolution in the consumer electronics, how they have made so many things which were known to us earlier, they have made all of them redundant. We had the earlier days telephone, the public call offices. We used to go to the public call office, coin boxes, where you used to put the coins and make the telephone calls. And even in our era, we were booking trunk calls to the different cities and international calls. And then we had Walkman, where we can use the cassettes, the magnetic cassettes, based cassettes. And we could listen to whatever we want, songs or talks or whatever. Then we also, there at one point of time, the tape recorders were a craze, the different type of tape recorders, the Panasonic, the Sony, you have heard all these names. And the maps, the paper maps, maps made by Survey of India, maps made by different tourism development corporation, state maps. We used to catch hold of all that and plan our itinerary if you want to go on a tour. And not to mention of the calculators. Casio, you've heard of the word Casio. Casio calculators, which have simple mathematical functions up to the quite complex mathematical functions like the sine, cos, and all that. And we have also the cameras. Different type of cameras, look and shoot, look and click, the film-based cameras, 120 mm cameras, the 35 mm cameras, black and white, color, chromes and all that. So all that has got replaced now. Now whatever you are seeing on the screen, they are all gone. They're all gone. They have been relegated to antiques. And all this function is done today by a mobile phone, and much more than what I have shown here. If you have a mobile phone, we say the world is in your pocket, right? We hardly see anybody without a phone, without a mobile phone. And the mobile phone, you can make basic call to anybody across the world. You can make video conversations, okay? And you can play songs, you can record songs, you can chat. And not to mention of the maps, you have the Google Maps, satellite-based maps available to at the fingertips. Calculator is all is so elementary functions which is built into this. And the camera. In fact, the mobile phone cameras are improving so much. They are giving the professional cameras a run for their money. You know, gone are the single lens reflex cameras and all that. Whatever the things you could get, you know, the filters and different kinds of photo, different settings, light settings, all that is available to you now in a mobile phone. So while you are familiar with this, I am going to take you on a similar journey of how the aircraft systems look like and how do they look like today and what is the impact of the evolution of the electronics into the aircraft systems. Yeah, go to the next slide. Well, the term avionic itself means any electronics used for aircraft systems for its operation. It is communication, maybe communication, the high frequency, very high frequency, ultra high frequency communication systems. The navigation, the radio navigation, inertial navigation, satellite-based navigation, different monitoring functions. We'll know more of these monitoring functions when we talk of the display systems. Aircraft flight control system. You must be aware today the flight durations are long flights, especially intercontinental flights. Take 16 hours, 20 hours. However, it causes a lot of fatigue for the pilot to keep on flying. Therefore, the total flying is taken over by the computers. You've got flight control computers on board. Once the pilot takes off and reaches a cruise altitude, he's going to hand it over to autopilot. And autopilot flies the aircraft for close to 16 hours, 18 hours, till you reach the destination. This is quite common. And it is done with the help of the digital flight control computers embedded with highly redundant and fully tested software. This is one area where the electronics has become flight critical. In the sense, the flight safety depends on the electronics. You have heard of the word black boxes. We'll see more of this later on. They have become famous or infamous whenever there is a crash, aircraft crash or an aircraft incident. People, the rescue parties look for these boxes. They hold the key to what happened, why the aircraft crashed. Weather monitoring systems. Earlier days, the flights were limited to the fair weather. It's no longer the case now because you're traveling for so long. The weather system itself can change, and the pilot has to continuously know en route what is the weather pattern and whether he has to take any action to maintain the safety of the aircraft. Aircraft management systems. The health monitoring is one of the key issues that has come up with the advance in electronics and computers. The health of the various onboard systems is now the monitoring of the health is taken over by computers. And you tell the pilot only when something goes wrong. Otherwise, the computers keep a tab of the health of the systems. This kind of systems are extensively employed to manage and monitor the health of various systems, electrical system, hydraulic system, fuel system, environmental control system, and so on. All the systems, health is monitored and the computer keeps a tab. Then the radar and sonar. Radar and sonar fall into the sensors. There are a lot of sensors on board. We'll have a look at it later. And these radar has various functionality depending on how you use for civilian use, for military use, and all that. And you've got electro-optic systems as well. Go to the next slide. Now, what we will do is, when you actually take the foundation course, we are going to spend a lot of time on explaining each of these. But now we are going to give you a bird's eye view of what is it you are going to learn in the foundation course or the internship course. So the presentation will be brief, but I'll cover the salient important points. But you're always welcome to join the orientation course to know if this subject interests you. You want to know more about this. Questioning is one. Question and answer session is anyway there. But if you want to know more, you're always welcome to join the foundation or internship course. So the communication system, the basic, what is the objective? Objective is to provide a reliable two-way communication between aircraft and ground crew, and also between the two aircraft when they're flying. In its very basic block diagram, very basic elements of the system, you've got a high frequency oscillator and you've got a modulator. The modulator modulates the audio signal which has the information. And the modulated wave is transmitted using a transmitter antenna. Then on the reception side, receiving antenna receives the modulated signal. Then you're going to demodulate it and you are going to feed it into a receiver. You would have heard of the word, especially the people coming from the electronics and communication background. You would have heard of the word super heterodyne receiver, which is very popular. And you have a very high fidelity receiver which decodes the signal and converts an audio signal. It will extract and give to the pilot headset. This is the basic functioning of a communication system, but the communication system itself can operate in different frequency bands. If you look at the frequency bands, the frequency band, whenever we say this frequency pertains to the carrier frequency or the high frequency oscillator, what we are told there. So it can be 2 to 20 megahertz, we call high frequency systems, and 100 to 200 megahertz we call very high frequency systems or VHF systems, and 225 to 400 we call ultra high frequency systems or UHF. And the latest in this is the satellite communication system. But irrespective of the frequency used and the technology used, the basic objective is the same. The basic objective is to provide a reliable two-way communication between aircraft and the ground crew, and also between the two aircraft. But if you go into the military domain, things become slightly more complex because you'll have to provide coding. Therefore, you don't, anybody who intercepts this communication should not understand what is happening. And you also provide anti-jamming, because if you jam the communications, then it's one way of crippling the whole system. So you'll have to provide systems which operate in the jamming environment. We call anti-jamming communication system. These are, of course, specially used in the military domain. Go to the next slide. Then we come to the aircraft navigation system. See, the navigation system basically addresses two fundamental questions. Where am I now, which we call as present position, and where I need to go, which we call as the destination. Suppose I ask you a question. I ask you students a question, where are you now? You will reply, you are sitting in the conference hall of the Sambhram College, Sambhram Institute of Technology. And where you need to go, at the end of the whole day session, you will need to go home. That's what you will say. But the computer will not understand this. Computer will not understand either the Sambhram Institute or your house. It won't understand. Therefore, you have to give this information in a way, in a standardized way, which is accepted all over the world and which the computers understand. Right? Just like you have got computer languages. There are different languages for programming, right? You don't talk to computer in the same way you're talking now. You employ different languages. Similarly, here, you employ different systems. to tell the computer these two basic information, where am I right now, where I need to go. But two very popularly used systems, and this is, we use two different coordinates, similar to, you're all familiar with Cartesian coordinate system, the XY. You can locate the position of a point on a graph paper, for example, with reference to the origin by an XY coordinate. Similar to that, in this type of system, one type of system, we use the latitudes and longitude. You would have heard of the word lat long for short. The latitude and longitudes are imaginary lines which are running across the globe. Okay, you have heard of the word equator, which divides the globe into northern hemisphere and southern hemisphere. And there are lines which are running east-west, parallel to the equator, starting from the equator up to the North Pole, starting from the equator up to the South Pole. These are called as the latitude lines. And the longitude lines run at right angles to this. You would have heard of the Greenwich meridian, you would have heard of the international date line. And they go from 0 to plus 80 or 0 to minus 80, 0 to 80 on the eastern side of the prime meridian, 0 to 80 on the western side of the prime meridian. Therefore, it is possible to locate a point on the surface of the Earth by means of a set of latitude and longitude coordinates. Okay, go to the next. The other system where you can see, you're familiar with the polar coordinate system. That means I can always, with reference to origin, I can say, I am at so-and-so angle. Suppose you draw a line at an angle to the XY intersection axis. And you can always say, I am located on this angular line at a certain distance, r. Therefore, this is known as the r theta. R theta is the radial line and the angular angle to the coordinate system. And XY axis. This type of systems which give you the range and the bearing. There are different navigation systems which operate on this principle, especially the radio navigation systems operate on this kind of principle, where they will tell you here is your location with reference to a ground station, at what distance you are there and what angle you are there. Okay. Therefore, this calls for a knowledge of the magnetic headings, magnetic north, south, east, west, and also the bearing. The word bearing we use to tell you are at what angle with reference to a point of your interest. In this case, a radio station from the ground. Okay, go to the. This slide basically sums up whatever we have been talking till now. The navigation system, if you look at the classification, the pilotage and dead reckoning are nothing but, in the navigation, the fundamental equation on which you operate is the speed, the time, and the distance are all related. You're traveling at 50 kilometers per hour speed, you travel for 1 hour, and you know that you have traveled for 50 kilometers, right? This type of principle is used even in the pilotage, even in the aircraft also. This fundamental thing is used, but it is very, very crude because you'll have to take into consideration the effect of the winds, crosswinds, and all that is going to drift the aircraft. And well, you are all aware of the celestial navigation. People used to navigate in the very early days before the advent of all this using the stars. During the daytime, sun rises in the east and sets in the west, therefore you know the direction east-west broadly. At night time, similarly, depending on the time of the year, you can look at different constellations. The group of stars are called constellations. These constellations appears in the sky and they appear at a certain location, specified location. Therefore, it is a science by itself. Knowing the detail, you can always find out which is the north, which is south, west, and all that. Broad directions you can know. This was also used extensively by people who are navigating early days, with ships, boats, and all that. But coming to the aircraft now, the two types of navigation, or the three types extensively used, are the radio navigation. Radio navigation depend on the ground stations. The ground stations continuously emit radiation which is intercepted by the aircraft to give the information that the aircraft is located in relation to the ground station at a certain angle and at a certain distance. There are some systems which will give you only the bearing, that is angular information. And there are some systems which will give you only the range information. And of course, for total navigation, you need both. ADF, VOR, and DME, for example, they will provide only the bearing information. And the TACAN, tactical navigation, provides the range and the bearing information both. LORAN and Omega C, which is called hyperbolic navigation, extensively used by ships, not so much by the aircraft. And precision landing aids, we are going to talk about landing aids in detail, the instrument landing systems and all that. And coming to the other side, you remember radio navigation extensively relies on the ground stations that are located on the ground. Therefore, you require an external aid for navigation. As opposed to this, the inertial navigation is totally self-contained. It doesn't depend on any external help, and it is used on it is determining continuously the latitude and longitude. Using that, you can navigate to any point on the surface of the Earth. There are two types of system, the platform-based and the strap-down-based. You will know more when you take up the course. And finally, you have the satellite-based navigation system, where you extensively rely on a group of satellites which are continuously orbiting the Earth in different orbits. Therefore, these satellites continuously transmit their position. Therefore, by knowing your position with reference to the satellites, by intercepting the signal from 3 or 4 more satellites, you know where are you with reference to the satellites. And you know where is the satellite with reference to the ground. Therefore, you can compute by software where is your location in reference to the ground. Okay, next slide. Yeah, now let us look at the landing aids. The landing aids, you see, the most important thing which the pilot requires for landing, when he's coming for landing, is the runway. Okay, these runways are designed to facilitate the landing of the different aircraft. Not all runways can handle all aircraft. There are small runways which can handle only small aircraft. The small and the big, we mean the weight. Weight is a crucial parameter. Therefore, even if you recollect, if you want, when there's a big aircraft like the Boeing 787 and the Airbus 380, when they wanted to land in Indian airfields, they were all strengthened. The runways were strengthened to receive these aircraft. So, in the early days, if you can't see the runway, you abort landing, you don't land. You may not see the runway because of the weather. And night you can see the runway by lights. I'm not talking of night. If the weather is good, we will also see the lights during the course of the discussion. And basically weather. Therefore, the earlier days, all the landings were limited to the fair weather. Fair weather, you see the runway and you land. But that is not acceptable. With the air traffic growing so much, you are doing all the number of flights have increased, traffic density has increased, number of passengers taking to flight has increased. Then you cannot always say, I will take off at one place in daylight and land at another place only during daylight. Not possible. Therefore, the electronic systems, with the improvement of the electronic systems, they are now providing a facility whereby you can land even if the runway is not visible, even if the runway visibility is 0. You don't see the runway at all. still they will facilitate you to land safely. So let us look at how this is done very briefly. You know, the runway is a strip of land which is well prepared, which has got a very definitive dimensions. It has got certain width and certain length, right? The length may be 3 kilometers, 4 kilometers, depending on where you are. And width may be, say, 500 meters, something like that. Therefore, it is necessary, if you are coming for landing, the two type of guidance is very important. One is you must be on the center line of the runway. Okay, you cannot go to the edge because beyond this width, normally the runways will have kacha land. Now, you have heard of a lot of accidents that it goes off the runway, gets into the muddy field and all that. Therefore, you have to maintain, you have to land on the center line of the runway. This is called as the horizontal guidance or the azimuthal guidance. These systems will provide you that are you to the left of the runway or you to the right of the runway and how to come to the center line of the runway. This is called as horizontal guidance. The other guidance is called as the vertical guidance or the elevation guidance. You know, you are coming for landing and let us say your cruise altitude 30 kilometers. And from 30 kilometers, you have to come down to 0, the elevation. Okay. And 30,000 feet, not 30,000 feet you are flying. From 30,000 feet, you have to come to 0 feet, that is the ground. And this you can't come abruptly. You have to come gradually. Right? Therefore, as the distance from the runway decreases, your height also must gradually decrease. Let us say at 20 kilometers from the runway distance, you are at a height of 30,000 feet. As you come closer, you should reduce the altitude very gradually. Therefore, what we say in technical terms is you have to follow a slope. There is an invisible slope from the runway. Normally, the international standard says at 2.5 degrees, or in some cases 3 degrees. There is an invisible line, and the aircrafts have to follow this line. They have to capture this line and follow this line. Then it will enable you to land smoothly. Therefore, this is called as the vertical guidance or the glide slope. Okay. This vertical guidance is provided by a system which is called as the glide slope. In addition to this, as you approach the runway, there are marker beacons at definite intervals from the runway. You have electronic beams that are going vertically up at 1 kilometer, 2 kilometers, 5 kilometers. When you intercept them, you will get definitive kind of signals. We'll see that in the next slide. All of them put together will give you the required guidance for the pilot to land safely. And depending on the decision height, there is a point in approach where the pilots must see the runway for landing. This point is at a specified altitude above the runway. It's called as the decision height. And the combination of the runway visual range, the distance at which you see, and the height. This combination of this will give you the different category of system. You can see here category 1 with the decision height of 200 feet and RVR, runway visible range of 2,400 feet. And category 2 is 100 feet and 200 feet, 1,200 feet. And category 3C is 0 feet and 0 feet. That means if you have a category 3C instrument landing system fitted in your airport, it will guide the aircraft up to the touchdown, even if the runway is not visible. That is what it means. Go to the next. So, well, this is going into the details of the system. It makes use of the two electronic beams, fan-shaped beams. You know, in the localizer, it operates on 108 to 112 megahertz, the VHF navigation band. There are two electronic fan-shaped beams, and at the intersection of these two beams is the center line of the runway. Therefore, if you are approaching the runway from the right-hand side, you will get one kind of modulation and one kind of display of the information in the cockpit, and also a different kind of audio signal. You've got a very unique kind of audio signal which is modulated at 150 hertz. If you are coming from the left-hand side of the runway, you get a 90 hertz signal, and if you are following the center line of the runway, you will not hear anything. So this is and there is a display also which is telling you are to the right of the runway or left of the runway. But remember, the job or the task of bringing the aircraft back to the central line of the runway is still with the pilot. Pilot has to fly it so that you come to the central line of the runway. Okay, this is not an automated system. It's not automatically bringing the aircraft to the central line of the runway. It's giving you the indication and the pilot has to fly. Next. Well, this is I'll tell you more about, this is about the glide slope, and similarly there are two fan-shaped beams, one above the slope, other below the slope. And if you're above the slope, you get one kind of indication. If you're below the slope, you get a different kind of indication and an audio signal. Therefore, the pilot has to fly to maintain this slope. Okay, go to the next. Yeah, this is the detail. Yeah, okay, yeah. The marker beacons. I told you about the marker beacons. They are directional beams going vertically up, located at different distances from the runway touchdown point. And the aircraft is coming, one is there on the center line of the runway. Therefore, if you are off the center line, you will not intercept the signals. After aligning your to the center line, maintaining the slope, you will encounter these markers. The outer marker, the middle marker, and the inner marker. They're located at different distances. They've got different modulations, and they will drive different lamps in the cockpit. Therefore, they are very similar to your railways. Railways, you got a, just before the train arrives at the station, it will cross an outer signal and then an inner signal, then it will come to the platform. It is something similar to that. Okay, go to the next. But before the advent of this electronics, these are all operating on the principle of electronic signals modulating a carrier and all that, whatever we say. But before the advent of that, and even today there are some very simple lighting systems. A set of lights are used to tell the pilot, but this is telling you basically about the slope, about the vertical guidance, not the horizontal guidance. Okay. The vertical guidance is telling you you are on the slope, above the slope, or below the slope. So this has basically it employs a set of very powerful lights. These lights are so powerful. During daytime, you can see them up to 8 kilometers, and during nighttime, you can see up to 32 kilometers. They're very powerful. And they are at an angle. They are at an angle, and the angle is the same as the slope angle, the 2.5 degrees. And as you come in for landing, initially you will see these lights as white lights. And as you come below these, there are not one light. There are normally a set of 4 lights. 1, 2, 3, 4 lights. Therefore, depending on whether you see these lights, if you are below the slope, suppose you are flying below the slope, these lights look red to the pilot. And if you are above the slope, they look white. Therefore, you have to maintain a combination of equal whites and reds to see that you are on the correct slope. Therefore, the mechanism of this we'll see later when you come to the course. But as he is flying, you can see on the right hand side, these lights can be either located in 2 rows, one behind the other as you are coming for landing, or they can be located side by side. So if you are seeing only white lights always, then it means you are flying too high. You are not you cannot land. You will fly over the runway and go off. Okay, if you are seeing all reds, it means you are not going to touch down on the runway, you are going to touch down much below before that. Before the runway, you will touch down. That means you are going to crash. So you should see the 2 white lights and 2 red lights to make sure that you are maintaining the slope. And in a system which is lights are located one behind the other, if you are in the same kind of thing is used, you should see a white light followed by a red light. Only red light will flash before the runway. If you see only white light, it will fly over the runway. This is outside the wrist. Sometimes they are located on one side of the runway, sometimes they are located on both sides. You can skip this slide because it's the same PAPI. Yeah. Now let us come to the development of the cockpit instruments and displays. See, nowhere else this impact of this electronics on the aircraft systems is visible, like you can see in the cockpit. Suppose you got 2 aircraft parked side by side. One is, let us say, a latest generation aircraft. It doesn't matter which aircraft it is. Another is an old vintage aircraft. Therefore, by looking, you will not know, by looking at the aircraft, you will not know what are the technologies that has gone into this. Correct? You won't know. It will look like 2 aircraft for you. But if you have peep into the cockpit, the station where the pilot is flying, immediately you will know. Immediately you will know whether what is the technology that is being used by this particular aircraft. Therefore, the impact of technology is most visible in the cockpit. So let us see how this has progressed. This is all about the information displayed to the pilot. So the pilot, when he is flying the aircraft, what is it that he needs to fly the aircraft? He wants information pertaining to the internals of the aircraft, that is aircraft and systems. Okay, this may be flight data. Flight data, we mean it may be speed, it may be altitude, it may be attitude. Attitude is a pitch and roll. Okay, or it may be an engine data. How is the engine performing? What is the engine RPM? What is the engine temperature? What is the engine fuel flow? It may be the data pertaining to different systems. Fuel system, electrical system, ECS, environmental control system, hydraulic controls, all that. That means the aircraft and systems data is presented to the pilot, which we call as internal to the aircraft. But this is not enough, because as soon as pilot takes off, okay, he should, irrespective of what is that aircraft, as soon as it takes off and reaches a certain altitude, he has to go somewhere. There is a mission. Correct? You are flying for something. Even if you are flying for joyride, that is also a mission. That means you take off and go around Bangalore and come back and land. That is also a mission. So it depends on what is the mission on which you are there. Is it a military mission? Is it a reconnaissance mission? Is it a marine cargo from one place to another? Or is it flying passengers from one place to another? Or is it training pilots? There are so many missions. So as soon as the aircraft takes off, the first thing the pilot needs to know information about the outside world. And what is it he needs to know? First thing is navigation. Where is he going next? Okay, you are taken off from Bangalore. Where are you going next? And how do you go there? Okay, you have to navigate the aircraft. And the second is he will require the information pertaining to the outside world by way of weather, and depending on the aircraft, you may have different sensors on board and all that. This information has to be presented to the pilot. And so remember, he has to be presented information pertaining to the aircraft and systems, and he should be presented information pertaining to the outside world. These are the 2 crucial things. This is true for any aircraft you take, irrespective of what aircraft you are talking. This division remains the same. Go to the next. Okay, now comes to the When you want to present this information to the pilot, what used to happen earlier days is each of these parameters used to result in an instrument. That means you want to depict the airspeed to the pilot. You have an airspeed indicator. You want to depict the vertical speed or the rate of climb. There is a vertical speed indicator. You want to tell the pilot at what altitude he is flying. You have an altimeter. You want to tell the pilot the attitude, the pitch, the roll. There is a gyro horizon. When you come to the outside world, you may have a radar on board. Therefore, you have to have a radar display. And you can have a forward-looking infrared. Infrared is extensively used in military applications. That image will be presented on the head-up display. Head-up display is is an electro-optic display, a very valuable display that has come where the information, the pilot is looking at the outside world through a set of transparent glass we call combiner, and the aircraft information also is presented on the same glass. Therefore, you don't have to take your eyes off the outside world. It is something similar to if you are driving a car. Suppose all the car parameters, people hardly look at the car dials. I know that. It is, you only look at fuel. Otherwise, you don't look at the speeds, you don't look at engine RPM and all that. But suppose you have to look at, then that information is presented on the windscreen, let us say. You're looking outside and driving, but you want to know what is the speed, you don't have to look down. You can look at one part of the windscreen, it is presented. It is something similar to that. But it is not presented on the windscreen. It is presented on a combiner glass. It is a part of an electric called head-up display. This is so useful now. It started off its journey in the military aircraft, but later on, even nowadays, the latest civil airliners also are using the head-up display, presenting information, especially during landing and takeoff, where they can't take their eyes off the outside world. At the same time, they need to know the systems information. Therefore, head-up display is used. And there are some specialized displays called laser displays and all that you present on the MFD. Go to the next. And we talk to the aircraft system, like engine system, fuel system, hydraulic, electrical, oxygen, so on and so on. These systems will present the parameters, which will tell you the health of the system. Engine system, for example, RPM, TGT, engine oil pressure, fuel system, you want to know the contents, how much fuel is there, fuel flow. Each of these resulted in an instrument. There is an RPM indicator, TGT indicator, oil pressure indicator, totalizer, so on, so on, so on. You have listed here itself about 20 instruments. Okay, go to the next. So what happened was it resulted in a cockpit. It looked like this. This, of course, is taken from Cessna. Cessna is a very a trainer aircraft. That's how you see two control columns and all that. But the front cockpit, if you see, we call the front instrument panel, you see a host of dials. You see a host of dials. Cessna is a very small aircraft. That aircraft has so many dials. So if you extrapolate, this is a single engine aircraft. If you got two engines and the instruments pertaining to the second engine also will come in. And if you look at a civil aircraft, which has got typically two engines or four engines also. You can imagine that the instrument panel will be cluttered with full of dials. There will be full of dials. And what the pilot has to do, pilot has to scan each one of them, understand what it is saying, and act accordingly. So you can slowly understand the complexity that is coming into the cockpit and how it is increasing the pilot's workload. Go to the next slide. Yeah, this will skip because this is pertaining to the standardization. You see, when the pilot is tasked with so much of so many instruments are there, then the people started saying that why don't you standardize the location of these instruments? Saying that I want, therefore the pilot will look at only his left portion, left top portion to look at the speed and things of this sort. We'll talk of this when you come to the course because it's not, we'll have to cover a lot of ground. We are only saying that the standardization came by way of the presentation of the information to the pilot in a certain location. Therefore, you can minimize his work. And the standardization was later on carried on to the electronic displays as well. That's the point that is important. Okay, go to the next. Now we'll come back to these instruments and try to understand the how you can present the information to the pilot. Okay, the classification of display is not unique by any means. It is one type of classification. You can classify them as a quantitative display and qualitative display. Quantitative display is you are looking at numbers. Okay, these numbers can be on a circular scale or a clock type of display like what you see, or it can be on a thermometric type of scale. You have got thermometer, vertical scales. It can just be a digital display. For example, your temperature, you can just say the temperature is so and so, 30 degrees centigrade, that's all, by way of digits. It can be any one of this. But they're all coming under the classification of the quantitative displays. You are displaying a quantity, a number. As opposed to this, especially in the aircraft, there are a lot of qualitative displays. What is qualitative display? Qualitative display, you are not interested in numbers, but you are interested in telling the pilot about a situation, about an event that has happened. What is that? For example, the undercarriage. As soon as you take off, you retract the undercarriage. You say the undercarriage is out and locked, or undercarriage is in and locked. This is one simple example. You're all familiar with the modern cars. Modern cars have got a door indications. Oh, we have got 1, 2, 3, 4, and the boot, 5 doors. If any one of them is not locked, you will see a red flag sticking up. That is not, it is not telling you any number, but it is telling you a situation, saying that the door is not locked. In the aircraft, extensively this type of display is used because they are very in a short space, but they convey a very important information. Go to the next slide. So you will keep on hearing this term glass cockpit, Glass cockpit only means a cockpit which does not have any conventional instruments, conventional electromechanical instrument. Therefore, a typical cockpit looks like this now. That's what I said in the beginning, that if you have a look into the cockpit of this aircraft, for example, it is like neat electronic displays, like TV screens are there. You don't find any, and if the displays are off, you will see them only as black screens. When they come to life, you will see different display symbologies. The display symbologies, they can be looking like a conventional instrument, but the technology is the active matrix LCD, AMLCD technology that is used. Therefore, they are neat, decluttered, and you can give the pilot what information he wants at a specified point in flight. So you don't require all the, if you want to give all the information pertaining to all the systems to the pilot all the time, then it results in a cockpit like what we saw. The cockpit is fully cluttered. There are so many dedicated instruments telling you about one parameters in the system. With the pilot, see, the pilot is concerned, his basic task is to fly the aircraft, right? Fly the aircraft, looking at the outside world, navigate and all that. So if there is a help which is keeping track of these parameters of these various systems, and tell him only if something goes wrong. Otherwise, you don't tell him. It's on-demand display, we say. On-demand means pilot wants to know something, he can always call for a display and see. Pilot wants to know the fuel system, what is happening. For the fuel detect the whole thing. That means presenting different display information to the pilot depending on the mode in which you are there. Let us say you are starting the aircraft on the ground. When you are starting the aircraft on the ground, you don't require, for example, his navigation, flight plan, all that you don't need. You require after the aircraft takes off. Right? Similarly, the weather report is available to you, but immediately you don't need, if you switch on radar on the ground, you will know ahead of you what is there. Ahead of you in a busy city like Bangalore Old Airport, if you switch on, you will see the buildings only. Buildings will reflect, right? Therefore, you need to have such information after you have taken off. So, at the startup, what you give you, what is important at startup? Engine. You have to start the engine. Engine has to come to life for you to fly. And fuel. You should know whether the aircraft is fueled, how much fuel they have got, fuel flow, is it flowing? So the engine fuel takes a very important position. You need engine information, you need the fuel information, and you need the ECS. If you've got an environmental control system, is it working? If it's not working, it is a no-go. You can't take off. Because you're going to fly at higher and higher altitudes, you need to maintain the pressurization, you need to maintain temperature, pilot comfort, passenger comfort, all. And similarly, you need communications. Okay, the basic communication is required. Even for starting the engine, you need to take permission from the air traffic control. So communication is required. Like this, they were on the ground, they gave this information. Once it takes off, you don't need the engine fuel information is being looked after by computer. If there is a problem, it will tell you. What is it you should know now? You should know navigation. Where are you going? Which is your next waypoint? How should I do? Should I turn? Your next waypoint may be to your right side. Suppose your runway is aligned to 00. That is the magnetic north. And your next waypoint is 090 at a distance of say 30 miles. Then you as soon as you take off, you have to turn. You have to turn right. You can't keep going on in the same direction. This kind of information is presented to him on the plan. And in more sophisticated aircraft, you will get a turning cue. You'll get a turning cue saying you turn right. You capture to go to the next way. Okay, therefore, this by switching out electronic displays, remember it is not just a display. Displays is you are seeing in the cockpit, right? But behind that, it means the system health monitoring is taken over by computers, and the navigation is taken over by computers, and the cue is presented to the pilot. Okay, go to the. Well, we see we talked of these parameters, but we didn't talk of the sensors. See the air data, for example, you want the airspeed, the altitude, bar altitude, and vertical speed and all that. You require to know the static pressure and the dynamic air. As the aircraft moves through the air, you need to know the dynamic pressure and the static pressure. You have to measure them and use this information to compute the airspeed and all that. Therefore, while the indicators you may replace and put an electronic display, the sensors remain as it is. That means you still need a pitot-static probe. And in the modern day aircraft, the pitot-static, in the earlier aircraft, the pitot-static probes used to be directly connected to the instruments in the cockpit by means of the tubes, by means of the process and all that. Don't do that. Very close to the pitot-static tube, you have air data unit, which converts this air data, which is a static pressure and the pitot pressure, you convert it into electrical units, and that unit is conveyed to a computer. You have a computer on board which houses all these equations that are required to break this pitot pressure and the static pressure into the individual air data parameters. You got the equations stored in the software. For computation, this you also need the total air temperature. So total air temperature probable data also is given to the air data computer, and the air data computer in turn creates the symbology for these different speeds and all that, whatever you want to present, and plays the display. Okay, I'm slowly taking you through how the cockpit has evolved, and not only how what pilots sees in the cockpit has evolved, how the technology at the back also has evolved and supporting this modern cockpit displays. Okay, go to the next. We will quickly run through these conventional instruments because when you when you go from this conventional instrument to the electronic displays, what happened to the air data instrument we just saw? I mean, you have an air data computer coming in. And similarly, what happens in this case to understand is the flight parameters, the attitude, basically, the pitch, roll, and the yaw. So in the earlier days, you had I'm not dealing with, in detail about gyroscopes. We'll do that when you come to the class, because we need to understand the principles of gyroscope. Gyroscope extensively used in navigation, and they are used in this conventional instrument. In this case, for example, a directional gyro is there. It has got a gyroscope whose axis is horizontal. Okay, this is presenting you the information of the aircraft movement in the azimuth or the horizontal plane. How much the aircraft has turned. Whenever we are talking the horizontal, azimuth and all, what should come to your mind is the compass. The compass rose what is being depicted here. Where is the aircraft pointed right now? Is it pointed south, pointed west? And when the aircraft turns, how much it is turning to the, what is the heading? We call it as the aircraft heading. But you can appreciate that the gyroscope will only tell you the aircraft is moved to the right or the left in the horizontal plane, but it has no information pertaining to the magnetic heading. It has no information. Therefore, if you want to make this instrument as a navigation instrument, you need to couple this with a magnetic sensor, which is normally done. Magnetic sensor, you got flux valve, which will give you the magnetic field, and or the meters are there, which will tell you about the magnetic Earth's magnetic field. I find this class instrument which says after you are taken off, you are now headed towards, in this case, for example, you are saying 210, sorry, 190. South is 180, you are saying 190, like that. Now you can talk in terms of the magnetic headings. Well, you may not be understanding all is understandable, but to give you if you hear this term and this whole concept, you can pursue this. That's the whole idea, is that if you don't understand 100% of what I talk, it's not of great concern, it's not an issue. Okay, go to the next slide. And similarly, we come to the horizon. This is, you have talked to the horizontal plane. Already the aircraft has got 6 degrees of more freedom, and you got 6 pitch up. You got 6 aircraft can direction, pitch up, pitch down, left, roll to the left, roll to the right, or yaw to the left and yaw to the right. The direction gyro is talking about the yaw. Okay, the horizontal movement, and the gyro horizon. This instrument is concerned about the movement of the aircraft in the pitch up, pitch, and the roll. Pitch up, pitch down, roll to the left, and roll to the right. Roll also we call also bank. Okay. So there is one gyroscope in this gyro horizon whose axis is vertical. One gyroscope is able to give you the aircraft movement in the pitch up, pitch down, and the bank to the left or bank to the right. And if you see the indication to the pilot, one important thing here is, in order to see figuratively, not literally, figuratively, if you are flying and you pitch up, what is it you see? You have to see sky. And the sky is normally blue in color. Therefore, the sky is reflected blue in color here. And if your aircraft symbol, there's an aircraft symbol here, and you find the aircraft symbol in the blue region, it means you are pitched up. Similarly, you pitch down at the ground, and the ground is normally brown in color. It's a notation that is used. Okay. Therefore, the notation is used, and if you are pitched down, you will see more of the brown in color. But remember, this is a synthetic display. This is not an actual display. That means you're flying at 30,000 feet, you pitch up, you may see sky as blue, provided if you ground, you may not see ground, and certainly you may not see the brown in color. Even in broad daylight, suppose you're flying over sea, you will not see brown in color. So the brown and the blue is used to denote are you pitched up or you pitched down. It's a notation. By immediately looking at this, you will know whether you are pitched up or pitched down. And similarly, but this is a very popularly used notation from the very early days. It is even carried out in the electronic displays, as you see in the coming slides. And similarly, this also is telling you instrument of go to bank to the left or bank to the right at the top. There is a bank angle scale. You can imagine the whole thing will rotate, and you will know the bank angle. Go to the next. Yeah, can you go to the next slide? Yeah, so what happens is, but these conventional instruments are removed now from the aircraft, right? In modern day aircraft, you find electronic displays. So what happened to these gyroscopes? Gyroscopes you still need. I told you sensors you still need. You can't get it. But you had one gyroscope for direction one. For example, you have navigation system and you are able to get this pitch roll heading information as an output from the initial navigation. I can take that, I can have a symbol generator unit and a data processor unit, which will drive an electronic display, which is configured as a attitude display or a horizontal situation display. These words have come now. Attitude display, electronic horizontal situation display. Why we have brought but now in the modern context, there is a lot more information in the vertical plane has come out. Right? Suppose you are using the top of therefore a vertical situation display. What is happening in the vertical plane apart from pitch and roll? What is happening from the ILS system also information I can present on this. Similarly, the horizontal situation. Horizontal situation was basically concerned with the movement of the aircraft in the horizontal plane. You are telling in terms of the magnetic heading and all that. But we talked of the navigation. Remember, the large number of ground stations are there, which are whose data you are getting, and you are trying to find out your information with reference to a ground station by means of the R theta or the lat long. This is in the horizontal plane. Therefore, you integrate that information and present a map to the pilot. Where are you? Where is the ground station? Either by way of R theta or by lat long. And also you can present at the landing time, you can present the horizontal guidance information onto this. Therefore, this is called as a horizontal situation indicator. This integration of different things started even before the advent of the electronic displays. But with the electronic displays, the integration became complete. Next. See the electronic attitude director indicator. This is how it looks like. This is a 5x5 active matrix LCD. And at the center, you find this sky ground shading again. You saw that? Sky ground shading is there. And then you got this qualitative displays. You get only symbologies you are seeing here. Right? A pitch ladder is there. And below it, you got a heading scale. What you are saying, 31, 32. We don't write the heading as full number. We won't write 310, 320 and all that. Even though the heading, magnetic heading is from 0 to 360 degrees. We don't write the large digit. Basically, from the point of view of decluttering. You got a very small size display where you represent a lot of information. We declutter that. It is again a notation that is used. Therefore, the last digit is not used. And similarly, you see the strip scales on the left-hand side and the right. The left is the speed. You put the speed on top. And the speed, not only it indicates the speed, you can also indicate the band. What are there is a speed below which you should not fly because the aircraft is going to stall. And there are similarly speeds you should not exceed. Then you can give the red bands at the bottom and at the top. There is a pointer which moves around to tell you what is the speed. Similarly, the altitude. Altitude on the right hand side. Again, here you don't write the full altitude. You write the current altitude. You see a window, small window, right? Above and below this window, you write only 3 digits, 215, 210 and all that. It means 215 means 21500, 21,500 feet. At the bottom, it is 21,000 feet. But the current altitude is 21,300 feet. That alone, you put it in a window. This is again a notation that's made use of. And you got the bara altitude, the above the ground level, above the sea level, and all that kind of information is available. And what you see below speed as 0.670 is a Mach number. Mach number means the ratio of your current speed to the speed of sound. This is also an important parameter. Okay, move to the next slide. This is the horizontal situation. Horizontal situation, as I was telling you, it is basically oriented around a compass. But look here, if you want, we want to declutter now, right? Therefore, the compass, only the frontal segment is depicted. If you have got a conventional segment, you add 0 to 360 degree full dial. But from the point of view of declutter, I will present only the front information from 180 degrees. 180 degrees. And you see the what is DTK, direct track and all that, direct track, time to go, navigation, all navigation information is presented on this with the what you are seeing at the top as a synthetic runway, that was also coming from the ILS, instrument landing system and all. Okay, on this you can depict where is the radio station, what is my magnetic heading, what is my true heading, and things like this. Okay, go to the next slide. We come to the recording systems. We need to give a break at some point, or we can cover this. It may take another 10 minutes. Professor Ravishankar or Anupama?
Sir?
Hello?
Sir,
Yeah,
can we have a break for 15 minutes, sir, now?
Yeah. That's what I was asking. We can have a break, no problem.
Okay, sir.
We can
Okay,
have
sir.
a break. We'll give a
Okay.
break. It is
So,
about
dear
11.
participants,
Yeah.
okay, sir. Dear participants, you can take 15 minutes break. Again, you can relog in by 11:20. Okay. So, but
Fine.
don't end the session.
11:20,
If you want, you
okay.
can leave the session. The session will be as it is. And if you are having any doubts, please put it in the chat box. Please don't end the session. If you want, you can leave. Afterwards, you can rejoin by back.
Yeah. So we'll start the session by 11:15. Is it okay? I mean 11:25?
Now, 11:20, okay. Okay, 11:20, sir. It's
11:20
already
is okay.
11:10 now.
Yeah.
Okay,
Yeah.
sir. Okay.
Okay. All right. Okay. So
Thank
we'll
you,
take a
sir.
break now. Thank you.
Okay, sir.
Okay.
We'll start the session now, sir. Shall we start the session now, sir?
Madam, 2 minutes, madam.
Okay, sir. Okay.
Hello?
Sir,
You're able to hear now?
yeah, we are able to hear, sir.
We can start now?
Yes, sir.
Okay, all right. So we had a look at communication, navigation, and the landing aids and displays. We'll cover the other important systems now, where the evolution in the electronics has done wonders. Okay, one of that such system is the recording systems, which we popularly call as the black box. And as you can see, it is not black in color, it is actually orange in color. It's painted orange in color. Why orange in color? Why orange in color? Because orange catches your eye. If you are looking for this box, after the aircraft has crashed, you have gone to a crash site and people are looking for this box, an orange color easily catches the eye. That's the reason. Of course, there are other ways of locating this aircraft which we'll cover. Basically, there are two recorders. One is called as the cockpit voice recorder, other is called as the flight data recorder. As you can see here, the function of this recorder is to record all audios in case of CVR and all data in case of FDR. But the most important point is this unit must survive the crash. You can keep on recording, that's fine. Throughout the flight, you can record. But when the aircraft crashes, let us say, and this unit also is destroyed, then there is no point. Therefore, this unit is designed in such a way that it will withstand the crash. How is it done? We'll just have a look. Can you go to the next slide? Well, the cockpit voice recorder is taking all audio inputs, the pilot voice, the co-pilot microphone inputs. There are cockpit area microphones are there. Those microphones, and the system generated, this will see what are they in the next landing system. And the instrument landing system, ILS, when you come, you will hear a lot of audios pertaining to the marker beacons, pertaining to the runway alignments and all that. All that information, everything is, there is a signal conditioning and processing unit. It does the analog to digital conversion, it does the filtering, it does the amplification, and it is a data acquisition unit it will give. And through the data acquisition unit, it is input into a solid state memory. Okay, this memory in the earlier days was a magnetic tape, therefore it had a limited period. You could record only up to 8 minutes, something like that. And after 8 minutes, you continuously rewrite. Therefore, you only have the last 8 minutes data with you. That is how it was. Now, such a limitation is not there because you have gone to a solid state memory which can hold data up to typically 25 hours of flight. Okay, this memory is put in an enclosure. Solid state memory is enclosed in a box which is fireproof, waterproof, crash-proof, enclosure made out of titanium alloy. So in case of fire, this enclosure doesn't get destroyed. And in case the aircraft crashes in water and you find this unit going to the bottom of the ocean, there will be enormous water pressure on this unit, and this unit will withstand that pressure. And there is a crash impact when the aircraft crashes, you'll see a lot of G forces, crash impact on this unit. It will withstand that. It is designed to withstand all this. Okay. And it also has a locating beacon. A locating beacon is there, we call underwater locating beacon, which will enable you to locate this unit under the water, even on the ground also, on the surface of the earth also. This locating beacon continuously emits a signal. It continuously keeps on emitting a signal, and this is powered by a battery. This battery also has got typically 25 to 40 hours of life. And this battery becomes operational once the unit comes into contact with water or once it experiences this crash impact. It starts operating and it will emit a radio signal. or a sonar signal if it is underwater. And the rescuing parties will have the corresponding receiver which will enable them to locate this unit. The idea is the unit, this solid state memory or the recording unit enclosure is announcing that you come, this is where I am. It's continuously giving out its location to help the rescue people to come and pick it up. And once the unit is picked up, if the unit is available, then you decode this, you replay this data, what was stored prior to crash, and then you reconstruct what happened. Reconstruct what has happened to find out the cause of the crash. Now the question is, why should you know why the aircraft has crashed? The aircraft has crashed. There is no way you can undo that. It is very important to know because the aircrafts can crash due to a variety of reasons. One very common reason is the weather. In spite of all that we said, suppose the pilot is coming for landing, at that time the weather is bad and there is no diversion possible because when we are running low on the fuel, if you know very well ahead and you know there are diversionary airfields are also planned while you do the flight plan. But during the landing phase, suppose he may not be able to take off again and go to a diversionary airfield where the weather is good. Therefore, he may be forced to land. And the weather is bad, it may be subjected to lightning, or the visibility may be very bad, or the runway, there is a runway is under some half a feet of water or so, the braking will be bad. It may overshoot the runway. So many reasons are there. Therefore, the weather is one factor. There are a large number of accidents have happened due to bad weather. The second reason is pilot error. In spite of all the training that they have undergone, the flying that they have undergone, but still they are human beings and they can make mistakes. There are, in fact, when you come to the, if you do take this course, I'll be dealing with some case studies for each one of them. Okay, and especially the pilots during landing, they'll be under high stress. Therefore, whenever we see, whenever we wish a pilot, we say happy landings. Okay, meaning that the landing is more important than the takeoff. Takeoff you can do, but landing is, you will have to, pilots, in spite of all the training they have undertaken, they will be under some kind of stress during landing. Okay. Therefore, the pilot error is one reason, weather is one reason, and the third reason is, if you look at the percentage, this percentage is very small, but nevertheless it is also there. That is the system malfunction. But nowadays there is so much of redundancy is built into the aircraft. The system malfunction has very few accident cases are there where due to a system malfunction the aircraft has crashed. The unit may fail, one unit may fail, but that does not lead you to a crash. It can lead you to a degraded functionality. Therefore, you got a lot. When you come to the course, we will deal with how the redundancies are provided. Navigation, if you take, you don't rely on only one kind of navigation system. It is very common for civil airliners today to have a radio navigation, to have an inertial navigation, and a satellite navigation. They have got multiple dissimilar redundancies. Therefore, you don't depend on any one kind of system. So, due to a system failure, the aircraft crashing is it is becoming rare nowadays. It was there earlier days, but it is becoming rare. If you take power generation, you got the redundancy, you got more than 2 generators and more than 2 kinds of pumps, hydraulic pumps, fuel pumps, on and so forth. So there are enough redundancies are built into the system design Therefore, a system failure or LRE failure cannot cause a crash. Having said that, there is one important element, and that is the software. Okay, because our dependence on software has increased. From whatever earlier days, our dependence on computers and software has increased. The softwares demand a very rigorous testing to iron out all the bugs, the software bugs. It will be plugged, and we do a rigorous testing. Even then, some latest crashes which have been around for some time shows that a software bug can cause a common mode failure. It has led to some crashes. Okay, the point is you should know why the aircraft has crashed. Very important. Therefore, the recorders go a long way in helping the designers to find out why the aircraft has crashed. Therefore, you can correct. Can you go to the next slide? Can you go to the next slide, Aishwarya? Yeah. We are talking about flight data recorders now. On the previous slide, we talked of voice. In fact, some interesting cases also we will deal when you do take the course. There have been cases where there is the ATC, the air traffic control, which actually facilitates the aircraft to land. There is a continuous communication between the ATC and the pilots. There are cases in which the pilots have not understood what ATC is saying, and they have done the wrong thing. Okay, this kind of cases also are there. So similar to the voice, the flight data recorder is another recorder where all the data, you see, you are now familiar with the parameters, aircraft parameters. Okay, aircraft, all the flight parameters, the data is stored. Aircraft flight parameters, for example, what is the speed, what is the altitude, what is the attitude, the rate of climb, acceleration, heading, control surface positions. They're all flight parameters. And similarly, engine parameters like the engine speed, fuel flow, turbine temperature, exhaust gas, etc. Output from various sensors on board. And all these type of data can be analog, it can be discrete, it can be digital, it can be data bus. All this is captured, multiplexed, they are converted to a suitable format and stored in the solid state memory. Remember, this is a different unit. Cockpit voice recorder is one unit, flight data recorder is another unit. Both are crash worthy. Both are designed to survive the crash. Therefore, we need to pick up both these units from the crash site and analyze the data to understand what has caused the crash. This is a very, very significant improvement in trying to analyze the flight data and establishing the cause of the crash. Next slide. You remember we were, while talking to the display system evolution, we talked of two kinds of parameters. One is related to the aircraft and systems. Other is related to the outside world. Pilot has to be presented with the aircraft and system information. Other is presented to the outside. Similarly, when you come to the warning philosophy, there is a need to present the information to the pilot pertaining to the not the warnings pertaining to the aircraft and systems, that is internal to the aircraft. And you also have to present to the pilot if something is going on in the outside world. Therefore, we are talking of two types of warning systems. The centralized warning system, what you are seeing now, is its major focus is on inside the aircraft and its systems. We have now seen that the routine monitoring of the health of the aircraft systems is entrusted to computers, right? And the computers, there are so many. Typically, you may have 25, 30 computers on board. And they manage different systems. For understanding purpose, we are told here an engine computer, flight control computer, system computers, avionics mission computer, and things of this sort. What all these computers do is they interface with a centralized warning system processor. Right. And the warning system processor has under its control three things to warn the pilot. One is a master caution light, what you are seeing at the top, red master caution light. The second is the warning panel, and the third is the headset, pilot headset.
Sir, is there any problem?
Madam, a minute, I'll check it and I'll keep updated.
Okay, sir.
Madam, 2 minutes. Power breakdown is there.
Okay, sir. No problem, sir.
Yeah.
Hello?
Sir.
Yes, sir.
we are
Are you able
audible,
to
sir.
hear?
Yes, sir.
Yeah, okay, fine. So, can you go to the next slide, Aishwarya? Yeah. So, we are seeing here that there is different computers, the engine computer, flight control system, and avionics. What they will do is they are responsible for generating the warnings. Engine computer is responsible for generating the warnings. It is continuously monitoring the engine health. And if there is a TGT, temperature is high, oil pressure is low, or FADEC engine control is lane 1 has failed, whatever it is. Therefore, they have got a set of warning conditions under which they will signal the warning to the centralized warning system process. Same thing with flight control, same thing with all other computers which are interfaced with centralized warning system computers. They signal the warning to the CWS processor. Can you go back one slide, Aishwarya? Can you go back to this? Yeah. So you're seeing here, these are the computers which signal that there is a problem. And what does the centralized warning system processor do? What it does is, it will first flash the red caution light. It is a caution light, a blinking light, which is located in a prominent place in the cockpit. It starts flashing to catch his attention. And it will also generate an audio, and the audio can be, see, the warnings itself can be classified as flight critical warnings or safety warning, and you can have different type of audio tones. Therefore, you are going to get a different type of tone in the pilot headset. Okay, but this master caution light and the pilot headset are shared resources. That means they are common to any warnings happening to any system in the aircraft. Therefore, what the pilot has to do, he will acknowledge the warning by pressing the master caution light. It has a switch, you acknowledge the warning, then the master caution light stops blinking, the audio warning will go away, but the warning has not gone. The condition which triggered the warning remains. Therefore, that warning condition which has triggered is parked in this warning panel, what you are seeing. The warning panel has got a set of lights which are a red light or amber light or different colored lights. It will tell you the warning condition, and that light will on the warning panel will remain on so long as the warning condition is live. Okay, this is the very brief functioning of the centralized warning system. You can go to the next slide. Yeah, go to the next. Yeah, so this is about the warning system pertaining to what is happening inside the aircraft. But there are the conditions can go bad outside the aircraft as well. Outside the aircraft, what can go bad? Suppose there is a system problem and the aircraft is continuously descending. Okay, or it is descending at a high rate of descent. You are supposed to descend at a design rate of say some 10 feet per second, for example. Due to some reason, system malfunction, whatever it is, you are descending at a higher rate. It means you are approaching the ground faster than what you should. Therefore, there are systems, there is a system called as the ground proximity warning system. The ground proximity warning system, its focus is on, is the aircraft likely to hit the ground in the next, say, some 3 minutes, 4 minutes. It is addressing this central question. For answering this question, it is getting the flight data, it gets the radio altimeter data, it takes the GPS data, it takes the ILS data, it also takes the terrain database. That means depending on the terrain the characteristics of the terrain are different around the world. Therefore, depending on where you are landing, this is basically crucially during the landing phase. During the landing phase, if you have input that airfield, I am landing at so-and-so airfield, then that airfield characteristics, what are stored a priori in the system will come, and that is also considered. For example, there may be airfields which are located on the seashore, on the waterfront, or there may be airfield surrounded on all the sides by hill. Airfield may be in the middle of at the bottom of the well kind of a thing. Therefore, there are different scenarios available. This stored terrain database also is used. And another point is, suppose you are taking off from an airfield which is located in a place where surrounded on all sides by hills. As soon as you take off, you must climb enough. You must climb faster to create the mountains which are ahead of you. Therefore, if your rate of climb is not enough, then also the system will determine you are going to crash into mountains. Therefore, it will warning. This kind of warning in the class when you come, we have got different videos for different modes of this system. One very popular warning all of you might have heard is the pull-up warning. It is continuously telling the pilot, pull up, pull up, pull up. Continuously you will hear in the headset. This is a synthesized warning to tell the pilot that he should pull up. And due to some reason, he is sinking at an excessive fast a more sink rate. Then it says sink rate, sink rate, sink rate. It will continuously telling. And coming for landing, you are not lowered the undercarriage due to some reason. Then it says lower undercarriage, lower undercarriage, lower undercarriage. And these kind of warnings are given to the pilot. Therefore, this is telling you about what is happening on the outside. Can you go to the next slide? Another important warning which has been made mandatory in all civilian aircraft is known as the Traffic and Collision Avoidance System. We call TCAS, Traffic and Collision Avoidance System. This system is continuously focusing on, is there a possibility of a collision in the next, say, 40 seconds or 60 seconds? Hello, Nataraj?
Yes, sir, your voice is audible now.
Audible. Okay, all right.
Yeah, it is audible.
Yeah,
Okay,
okay,
sir.
fine. So this traffic collision avoidance system is continuously focusing on generating instructions to the pilot and telling him if there is a probability of a crash, of a collision. Remember, this is only terminal guidance. That means you are worried about this only when takeoff and landing. You are not worried about this when somebody is cruising at 30,000 feet. No. So how does it do? How does it do is it is has got a transponder. You remember it can transmit an information asking the aircraft in the vicinity. This is during takeoff and landing. It has got a transponder which sends out a signal or an interrogation to the other aircraft in the vicinity.
Prasad sir?
Hello?
Yes, sir.
Yes, sir.
You're able to hear now?
Yes, sir.
Yeah, we'll continue.
Yes, sir.
So, this traffic collision avoidance system sends out the interrogation during the transponder to the other aircraft, and all other aircraft will respond. What do they respond? They will respond where are they, what is their location, and what is their altitude, what is their flight plan, where are they going, things of this sort. Using this information, the aircraft which has initiated this will construct a three-dimensional map, and it will continuously update the map to find out whether there is any intruder. What you are seeing in the slide here on the right-hand side, is the intruder. The intruder is the one who is likely to crash into you. Therefore, it will generate two kinds of advisors. One is called as a traffic advisory if the aircraft likelihood of the aircraft colliding in 40 seconds. Another one is the resolution advisory if the aircraft is going to crash into you within 25 seconds. And it is mandatory for the pilot to obey the instructions, the resolution advisory especially, and act according to that to come over this situation. It may be climb, it may be a climb command, it may be a dive command, it may be a hold altitude command. Depending on the command, he has to follow the instructions, and this will have priority over the air traffic control instruction. Yeah. I think we have come to the end of this avionics now. Can you go to the next slide? Is it right, Aishwarya? We have come to the end of the avionics. And this we can skip. It's a block diagram. So if you have got any questions on avionics before we go to the electrical systems. I'd like to take the question because you will forget this avionics when you talk about the electrical system next. Are there any questions?
Students, if you are having any questions, you can ask or else put it in the chat box.
You can put it in the chat box also. There's no problem. We can take a look at the chat box at the end of the electrical session. Shall we go to the electrical now?
Yes, sir.
Okay, all right. So in the first session today, we saw about the avionics, how the improvements in electronics have helped, how that what are the various improvements that have happened in different systems, how it has helped the pilot, how it into the safety and all that. In the next 1 hour or so, we'll have a discussion on the electrical system. When you say the electrical system has got 2-3 aspects. One is the power generation. Power generation and distribution, what are the type of electrical generators you have on the aircraft, how their redundancies, what the way they're distributed and all. That's one very clear focus area. The second area is pertaining to the design of the electrical system wiring. See, because there are all these, whatever systems you have seen from the morning, they all will convey or talk to each other over electrical wiring in the aircraft. Therefore, the design of the wiring, and the third focus area is the manufacture of this wiring and putting it on the aircraft. So we will be focusing not on the first area. We will be focusing on the second and the third area, meaning the wiring, aircraft wiring design and its manufacture. That will be our focus area now. What we'll be covering? We'll be covering the aircraft different type of wires and cables. How do you select a cable? What are the type of cables? What are waveguides, thermocouple cables? And we'll come to, very quickly, we'll come to the aircraft wiring and what are the different type of wiring drawings. How do you design the wiring? How do you go about designing the wiring for so many complex systems, what you have seen? And how do you put it on the aircraft? How do you test it? And this area is electrical wiring we have chosen because tomorrow afternoon you have a session by colleague Madhu who will be talking of how can we, there is an app in the 3D experience platform. This platform, this app enables you to design the wiring and design the harness, that is the aircraft wiring portion. How do you actually fabricate it? How do you route this on the aircraft using a 3D experience platform? And how do you go towards manufacturing? What do you need for manufacturing that and all? That session is there tomorrow afternoon. So this session will serve as an introduction to that session. Okay, go to the next slide. We'll straight away get into that. If you look at the electrical wiring, basically electrical wiring, a large number of wires which are interconnecting the various units within the aircraft. The electrical wiring itself goes through these different phases. One is the design phase. The design phase, you are focused on the current, the selection of the wire, current rating, cable specification, environmental specification, and installation zone. Where are these wires routed? Is it routed in the fuel tanks? Are they routed on the engine? And are they routed on the undercarriage bay, the swamp areas, and things of this sort? And you also have to address the electromagnetic interference and compatibility requirements to select the suitable wire. And during the design phase, you also address the distribution system and also the loom drawings. The loom drawing, different type of drawings, they're all in the design phase. Okay. Electrical schematics, routing drawings, zonal drawings, loom drawings, panel drawings, they're all, you'll have to generate all this during the design phase of the wiring, aircraft wiring. Next comes the manufacturing phase. In the manufacturing phase, you require loom boards. For each harness or a cable bundle, you require a loom board, which will facilitate you to manufacture this harness and the loom fabrication and testing. And then once you're done on the bench, this on the bench, then you go to the aircraft. Aircraft, you route this harness, install it. Installing, you'll have to follow certain guidelines, the segregation to take care of the redundant systems and the battle damage and things of this sort. And you'll have to follow certain good routing practices. What are they? We will see as we go along. But once you have designed, manufactured, installed, then the integrity checks. You'll have to do end-to-end continuity checks, the mega installation checks, and what are automatic harness checkout systems to make use of, and the voltage standing wave ratio measurement for the RF and all that. Then of course you get onto the flight and the maintenance. Go to the next one. See, the wire, simply a wire means it's an electrical conductor which carries a current. That's the simplest definition of the wire. But these wires can be a single conductor. It can be multiple conductors. It can be a stranded conductor. There may be many strands. And they are surrounded by insulation, right? And protective materials, because we don't want this current carrying conductor to get shorted, to come into contact with ground structures and all. When we say cable, normally we mean these wires. There are two or more wires within the same insulation and a protective sheet. Why two or more wires? We will see if you have got two or more wires within the same insulation, they can be twisted and shielded, or there can be a triplex, three cables. This is all possible in cables. The conductor is normally made out of copper or aluminum, and the insulation is normally PTFE. PTFE kind of insulation is made available around the cables for protection against the possible chafing, abrasion, shorting, water ingress, moisture, and things like this. And if you look at the different type of cable that are used, you have got shielded and unshielded wires. Shielded means these cables are surrounded by a shielding material, because the shielding material acts as literally a shield against all electromagnetic interferences. Then you have thermocouple cables for measurement of temperature. Suppose you want to measure the inside engine temperature. You have got a hot junction and a cold junction. You use dissimilar metals. It operates on a principle called Seebeck effect. Means if you got two wires which are connected at one end to the hot junction, other end to a cold junction, two dissimilar wires, then there is an electrical current flowing between them. A voltage is induced between these two junctions. Therefore, using this principle, I can measure the temperature of the hot junctions. You have got data bus cables. different data bus are available in the aircraft. This data bus cable have got a special construction. And you got radio frequency cables, you got power cables. Power cables normally carry electrical power, therefore they carry more current, especially the cables connected to generator, where hundreds of amps of current is carried. The power cables can be very thick because the copper will be so much. Copper conductor will be so thick, therefore you'll have to take special precautions for routing those cables. Okay, go to the next. Well, this tells you the simply it's a American wire gauge, AWG, which is giving you what are the wire sizes, what is its current carrying capacity versus the temperature. This is a good design guide you make use of for selecting the cable, what gauge of cable you need to normally select. Now go to the next. Wire and cable is to be suitable to the type of application, and factors to be considered are voltage, current, ambient temperature, mechanical strength, abrasion qualities, flexibility, pressure altitude requirements, and so on and so on. There are very, very well laid out specifications available for you to select this cable. Okay, go to the next. See, the aircraft has different systems. You have seen that from the morning. It has got, say, flight control system, avionics system, lighting system, radar system, so on and so on and so on. These different systems have their own units within the system. And this unit is called as the line replaceable unit. You will keep on hearing this word very frequently. Tomorrow also you will hear LRU. These LRUs normally exchange the information with other LRUs within the same system or with LRUs of other systems. How do they exchange information? Electrical wires are used to exchange the data with either the same LRU of the same system or LRU of the different system. Now, I'm going to introduce you into the concept of the system designer. See, the system designer is the one who has designed the system, as opposed to an aircraft designer. An aircraft designer is one who is designing the aircraft, which has so many things. It has got structure, it has got systems, and it has got different elements. Okay. So the aircraft designer has to take care of all this. Has to take care of the aerodynamics is there, who has to worry about performance. Flight control has to worry like this. Flight control has to worry about not only the wiring, it has to worry about the flight control system design itself. Therefore, the system designer can be normally is different from the aircraft designer. System designer is focused on design, development, manufacture of a system. And that system can be used on any different aircraft. It can be used on 1, 2, 3, 4, 5 type of aircraft. Simplest example is a communication system. Communication system designer is an expert in designing the transceiver, the transmitter, receiver, the audio system inside super heterodyne receivers, its own PCBs, its own selection of VLSI, things of this sort. He is truly concerned about the design of the LRUs within the system, putting them together and making them they meet a system performance. This is his job. And the wiring is one aspect of the system design. Therefore, what the system designer will do, he will start by making a drawing which we call as a system schematic drawing. The system schematic drawing is made by the system designer, which will telling you the interconnection between the various LRUs within the system, and you can go to the next slide. It's also telling you the information like what is the type of signal, what is the source of the signal, what is the destination of the signal, what type of connector is used, what is the pin designation, what are the power requirements, is it AC or DC, and where should I give the power, what pin I have to give power, what pin I have to ground, and is it analog signal or digital signal or audio signal or video signal or RF signal, type of signal. All this information he puts down in a drawing and give it to us. All this information is required by the aircraft designer for selecting the wires. You can see that. Analog, you have to use some kind of wire. Digital, RF, you have to use some kind of wire. Power, you have to use a different kind of wire. And AC, DC, all this, if the signal is very delicate signal, you have to use different kind of wiring with lot of shield protection on that. This information is given to the aircraft design. Therefore, as many number of systems are there, so many number of system designers are there. There is a system designer for communication system, there is a system designer for flight control system, things like that. They make a system schematic drawing and they hand over this drawing to the aircraft design. Okay, go to the next. We'll come back to this slide. Go to the next slide. So the aircraft designer, what he does is he first prepares a theoretical drawing. What is a theoretical drawing? It is nothing but the adaptation of the system schematic drawing to your aircraft. What way it is different? What way it is different is these, depending on the system, there are standard specifications which say you have to use the system code to identify the LRUs in this system. If it is a radio system, you have to use the code R. If it is a flight control system, you have to use the code F. If it is a hydraulic system, you can use the code H. Like this, there is a spec available. You have to use the spec and identify the units in this particular system using this code. For example, all the radio system, for example, communication system, it has got 10 LRUs. You can say it is 1R, 2R, 3R, 4R, like that. Not only that, the unit, once you have identified, the unit has different connectors. One unit may have 3 connectors. These connectors also you need to identify. If it is 1R connector, you can say it is 1RA, 1RB, 1RC, like this. Therefore, you have identified the unit and you have identified the connector that is on the unit by means of a unique electrical identification code. Then this unit is drawing power from different electrical buses on the aircraft. These buses may be primary buses, battery buses, emergency buses, things like this. But finally, they draw power from what we know as a distribution box, and each of the services is protected by means of a circuit breaker. Circuit breaker is a protective device, like a fuse. We don't use fuse on the aircraft, we use circuit breakers. The circuit breakers also have to give the electrical code. Okay. Then you also have to identify the grounding points. The system designer is telling you this unit, this connector, this pin, you please ground. Therefore, I'll have to ground it on the aircraft, and this grounding or the earth stations are well identified in the aircraft depending on the area where they are located. Therefore, you have to identify the earth stations by numbers. Earth station 1, 2, 3, 4. If you put all this information, you get a theoretical drawing. Theoretical drawing is a adaptation of the system schematic drawing which is given to you by the system designer by allocating the unit code, by allocating the electrical code for the unit, electrical code for the connectors, and identifying the power points, identifying the grounding points, identifying the circuit breakers, things like this. This is the first drawing with the aircraft designer does theoretical drawing. Go to the next slide. The next drawing that the aircraft designer has to do is called as the routing drawing. What does the routing drawing do? The routing drawing addresses where are these units located. See, the aircraft, you may see an aircraft as a whole, but the aircraft, when you come for aircraft production, aircraft is not built that way. Aircraft is built in major structural assemblies. Front fuselage is one assembly, rear fuselage is another assembly, center fuselage is another assembly, wings are another assembly, fin is another assembly, nose and things like that. Undercarriage is another assembly. Why it is conceived, designed that way? To speed up the production, these different major structural assemblies can be given to different people, different companies. Therefore, they can all be parallelly doing that. Finally, it will come back to the aircraft house for assembling all of them. When you do that, you consider wing, for example. The wing has got so many elements. It has got a structural element. Okay, it has got ribs. It has got the stringers passing on major longerons, and it has got the wing skin. It also, from what we are concerned here, is it also has lot of system components. Because normally all aircraft wings carry fuel. Therefore, the fuel system components, like the pumps, like the fuel gauging probes, like the transfer pump, booster pump, all these are contained in the wings. Okay, and wings also are the primary lift devices. They are the ones who produce the lift, and the control surfaces, the aileron, elevator, slats, they're all located in the wings normally, right? They have got electrical actuators. Okay, these electrical actuators have to carry wiring. So, and similarly, you may have some lighting system. You may have a navigation light at the end of the wing. Therefore, the navigation wiring will come there. So, a company or a vendor who is supposed to do the wing, who is supposed to manufacture the wing and supply it back to the aircraft, must also supply the wiring related to all these units. Correct? He has to equip it. When fully equipped wing, he has to give it to the aircraft. This is what is required. So what happens is, if you use this concept, the units or the LRUs belonging to different systems are located at different parts of the aircraft. Therefore, you may find these different LRUs in different structural assemblies. And the wiring that is related to this, it goes without saying, you need to provide a brake for these major structural assemblies. Right? When the wing is made, along with its wiring, when it is brought, to have the wiring continuity with the rest of the system, you need to provide electrical brakes. You need to provide electrical brakes for wiring, electrical brakes for the pipes, that is the fuel pipes and any other hydraulic pipes and things like this. So this routing drawing, what it does is, it will tell you where are these units located, and you introduce brake connectors in your drawing. Theoretical drawing tells you the wiring is going from one source to destination. The routing drawing tells you the wire is going from route to destination through these brakes, which are provided from the point of view of aircraft manufacturer. We are telling, for example, it can be a cockpit brake, it can be a wing brake, it can be an avionics brake. So what happens is, what you are depicted as a single wire in a theoretical system, when you route it on the aircraft, it can have 3 or 4 segments, 3 and 4 segments to go from source to destination. So each of the segments you identify by a wire number. This wire number identification also has got a notation. We are told here, for example, it says 20R101N, 20 talks you to the gauge. You are familiar with the gauge. R talks you to the system code, and 101 is the actual numbering. And if it is a ground wire, you have to use a suffix, which is N. So from system schematic, you come to theoretical, you come to routing drawing. Routing drawing is telling you all units by way of the electrical codes, all wiring by means of the electrical codes, and it is telling you Where are these units located? And it is flowing through what breaks, right? But the question now is based on these routing drawings, can you manufacture a wiring? The answer is no. Because you're not going to wire the aircraft. I'll not wire communication system, then I'll wire fuel control. It is not done that. Most inefficient way of doing. So what you do is you come to the concept of the harness. Go to the next. Yeah, it is reinforcing whatever I told you till now. The wiring you will have to fabricate all the wiring that is coming in the wing, for example. And we just now said it has got fuel system wiring, it has got flight control system wiring pertaining to actuators, it has got lighting system wiring. So this are therefore you'll have to practical brake, and from the brake you'll have to design the wiring going to these different units. The wires which go to these different units, you know what are the wires. You know how many wires are there, and you know starting from the brake connector what pin the wire is flowing to, what unit and what pin. How do you know? You know this information from the routing drawing. If you take a fuel system routing drawing tells you in this wing what are the units pertaining to the fuel system they are coming, what are the electrical codes, what are the connectors, what is the source and destination for this. And it is flowing through what brake connector it's telling. Same thing with others. Therefore, if you collate this information pertaining to all the systems coming in the wing and isolate the portion that is coming in the wiring, you have got a wiring that is coming in the wing, which starts from the brake connectors and fans out to different connectors on different LRUs belonging to different systems. Make sense? Yes. But the problem that is coming now is these units are located at different points in the wing. Nav lights are in the end of the wing. Okay, the fuel units are close to the brake. Okay, if you consider where you are seeing the brake connector, is where the whole wing is mated to the aircraft. Therefore, this portion is close to the center fuselage, and the wing tip is away from the center fuselage. Therefore, you can see the wire length is different. The length of the wire that flows from the brake connectors to navigation lights has to run throughout the length of the wing or throughout the width of the wing, whatever we call. And similarly, the wiring which is flowing from the brake connectors to different units in the wing have got different lengths. And if you don't know ಗೊತ್ತಾಗಿತ್ತಾ? Hello? Hello? Hello?
Yes, sir. Yes, sir.
You're able to hear?
Yeah, sir. Yeah.
Yeah, because
You can
there are
continue, sir.
some power interruptions are there in my
Okay, sir. No
place.
problem.
No problem. Yeah,
Okay, sir.
okay. So we have come to this task where from the brake connector, the wiring is flowing to the different units which are located in the different parts of the wing, when we need to find out the wiring length if you want to fabricate this harness. A harness is nothing but the wing harness. If you take, they may have 1 or 2 or 3 going from brake connectors flowing to different units which belong to the different systems. So how to find the length? This is where to find the length, people had used different techniques. In the very early days, people used to use on the drawing boards, you root. Drawing boards, you are familiar with 2D drawings, you root both elevation and the plan and try to find out the length. But other people made mock-ups. They built wooden mock-ups, located these units, located these dummy wires and find out the length. But you don't have to do all this now. Now the 3D experience is available to you. 3D experience as a platform is available where the structure, wing structure is available to you. Therefore, you load the structure, you locate the different units on the structure, and you can even route the wires. You can even route the wires using the 3D app that we have, which Madhu will talk to you tomorrow. So we have a 3D routing of the wiring of the units coming in the wing in the 3D experience. Aishwarya, can you go back to that slide which you skipped pertaining to the harness? Yeah, this is how it looks like. This is how the wiring looks like. It is starting from one connector, it is branching off, it is going to different connectors. You will get this 3D routing of the wiring either in any sub-assemblies, structural assemblies, or on the whole aircraft. Once you do, what do you do next? What do you do next is you go to the next slides. You go to the next slide and go to the next slide. Next is we'll have to flatten this. You see, you have got in 3D experience, you have got the wire routing, but in order to facilitate, in order to help you for manufacturing, you have to flatten this on a two-dimensional board, and this is known as the loom board. Therefore, what you do is you, for flattening and creating loom boards also, this app will help you. You create the loom board where the 3D routing is available to you on a two-dimensional board. And now this board is a tool which you can use for fabrication of the harness. But what do you need for fabrication of the harness? What you need is two types of documents are required. One is known as the material schedule or the bill of materials, where every wire that is coming, okay, you will have to say what is the type of wire, what is the length of wire. Because the type of wire can be different and length can be different. Each wire you have identified by a wire number. You say the wire number and say what is the spec, what is the length, and who is the manufacturer. This is enabling the person planning to procure them. Because the wires comes in rolls of 10 kilometers, 15 kilometers like. And then the other hardware that are required, the connectors which connect to the units, you'll have to list out the connectors for procurement. And then other things, the wire numbers are normally printed on the wire. But the connectors, normally you will have sleeves, protection sleeves, and for the whole harness itself, you need a protective sleeve. All the hardware you have to call in the material schedule or the bill of materials. Then another document tells you, it's a simple table which tells you what is the source connector, pin number, wire number, and what is the destination connector and pin number. You have to generate this document and you tell the type of termination. Type of termination means how do you actually connect the wire to the connector? Is it by soldering? Is it by crimping? You specify this also. Therefore, with the help of the loom board and with the help of the hardware drawing what you have made using the app like this and material schedule and the cable list, you can fabricate the harness on the bench. Okay, go to the next. Yeah, this is telling you the process. We can skip this slide. It's telling you in detail as I told you, it comes in rolls and all that. So once you have done the harness fabrication on the bench, of course you need to test it. You need to test it for end-to-end connectivity. You can use that cable is table to tell you this source to destination, this is the wire that is coming, you can do that. And then this harness which is fabricated to all specifications, tested, cleared, comes for installation. On that installation, you will have to make one more drawing. Installation is called as a harness installation drawing because you have already established the routing path. On the 3D, when you route the wire, you have established the routing path. With routing path, there are a lot of guidelines. You will have to follow very close to structure. You'll have to secure it to structure. You'll have to avoid sharp corners. If you are passing through a cutout, you'll have to provide suitable protection. Therefore, the wires don't get chaffed. You have routed the wiring. You have clamped it. Imagine the aircraft has got so many harness like this, right? You may have, say, some 500 harness. And after you installed on the aircraft, what you need to do? First thing you have to do is mate all the brake connectors. Because the harness are manufactured as independent entities. So when you install it on the aircraft, mate all the brake connectors. When you mate all the brake connectors, you have got a source to destination flow of the signal path you have, starting from the source, so pin to so brake connectors, and finally coming to the destination connector and destination pin. This, how much amount of information, this much you have installed. What next? What next is testing. Okay, this testing of the individual harness on the bench, you have tested and put it on the aircraft, but that is not enough. You will have to test it end to end. End to end, you will have to test it to see whether there are no mismatches somewhere. Because all this process of manufacture of the harness is manual. There is no automated process. So manual means there could be error, even though there are checks and balances at every stage, there could be an error. Therefore, you will have to do the end-to-end checks. Okay, what are the end-to-end checks? How do we do? We'll go see now. Go to the next. Yeah, these are telling you the clamps, it is proper kind of clamp, routing and all that it is telling you. Madhu will speak more of this. Go to the next drawing. We'll go to the testing slide. Yeah, hold here. See, I have taken you through the process of drawing. Correct? We came from system schematic drawing. We came to theoretical drawing. We came to routing drawing. Hello? Am I
Yes, sir.
audible? Yeah,
Yes, sir, you are audible now.
audible.
Okay.
So we went from this drawing side on to making the cable list and all that. But the disadvantage in this kind of an approach is one is you will be using different kind of things for drawing. You know, you may be using AutoCAD initially, then you may be using CATIA V5 for this and MS Word for continuity and all that. And the responsibility of ensuring the integrity between these various kind of documents rests with the designers. Okay, it has to be done manually. This is how it was being done about a decade ago, let us say. But now what has happened is now things are different. Now everywhere you latch on to a database based system. That means you don't create drawing first. You create a database first. That means once the system schematic drawing is given to you by the system designer, you create a database pertaining to all the connectors and the source and destination. Once you do that, then you can interface that to a tool which creates a drawing out of the database. For database creation, you require a separate software. It is not in the 3D experience. Let us say you have a software. Using the database, you can interface with 3D experience and generate drawings. The advantage of this is this database, what you have, you can use it for end-to-end continuity, what we see in the next automatic harness checkout system. You can use it for the whole aircraft. You can use it part of the aircraft. And it is easily amenable for checking the integrity. You can check the integrity of this data very easily by a database than a drawing. Then the change is easy. You change in one place, automatically it changes in other places. It's not so in the drawing. Therefore, the current approach is go towards a database driven drawing making system, which will help you a lot. So go to the next slide. We have come to, if you typically the wiring length in a fighter is about 40 kilometers and in a civil aircraft it can be 500 kilometers. Therefore, you can you can appreciate that we need an automatic checkout. You can't, there is no automated system for making the harness. It has to be manual. But there can be an automated system for checking the integrity end to end on the aircraft. And this is done through an automatic harness checkout system, which is a database driven system. You have the entire aircraft electrical connector pin data, the source destination pin stored in the computer, stored in the system. Okay, this is the database driven system, what we are saying in the beginning. The same database you can import into the automatic harness checkout system. It is a checkout system. It's not, it's a system outside the aircraft. It is designed to check the integrity of the wiring which is laid out on the aircraft. How it is done? Go to the next slide. In the next slide, you see the aircraft here. Aircraft, imagine the aircraft is full of wiring and connectors already laid out. You have seen how they are designed, how they are wired, how they are manufactured, how they are routed and installed on the aircraft. You have to only check the end-to-end integrity, end-to-end continuity, and the MEGR, the insulation resistance checks. So what you do, any particular harness what you have, which has got two ends, and you are checking the continuity between the pins of the various ends manually earlier. Now what you do, you mate them with electrical connectors and bring that out. That means the aircraft harness is still lying on the aircraft. The two ends of the harness, you take another set of two connectors, mate with them and must have come. You are able to hear now?
Yes, sir.
You are able to hear now?
Yes, sir.
Hello? Yeah.
Yes,
Okay.
sir. Yes, sir. You are audible
Anyway,
now.
we are in the last 5 minutes anyway. A lot of interruptions.
Okay, okay, sir.
So this using the automatic harness checkout system, you check out the end-to-end wiring on the aircraft, and it goes a long way in cutting down the time, testing time on the aircraft. Therefore, what used to take earlier 3 months, you can finish in about 4 or 5 days. Okay, go to the next slide. I think we have come to the end of this side. Go to the next slide. Yeah, these are all the racks and configurations and all that. Yeah, you can go to the next. Skip this. Yeah, so we have come to the end of this. Sorry for these interruptions and also this. I rushed you through this, and it is a very detailed design activity. Therefore, if the kind of activity interests you, it is a marrying of the electrical system with the 3D experience. A very interesting area, so to say. And if you take this course, you will know more about this. So I welcome you to ask the questions either on the avionics or on the electrical systems. Anupama, you can coordinate.
Yes, sir. Okay, sir.
Yeah.
Dear participants, anybody is having any questions? If you have any questions, please put it in the chat box. I think no questions, sir.
No question. Okay. No
Uh,
problem. No problem.
So now okay, sir. Now
Yeah.
I would like to thank Mr. HRS Prasad for his wonderful session. Our students will definitely make benefit use of it. Now you have a lunch break. You can log in back at 1:50 p.m. After the lunch break, Mr. Mandar Inamdar is going to deliver a topic on 3D experience FEM, that is Simulia. Thank you all. We'll meet you again at 1:50 p.m.
Thank you.
Yeah, thank you, madam.
Thank you.
Thank you, sir. Thank you so much.
Thank you. Thank you. Thank you.
So we'll end the session now.
Yeah, sure.
Okay,
Thank you.
right, madam.
Thank you.
Okay, sir. Sir, we'll start the session now.
Sure. Can you hear my voice clearly?
Yes,
Yes,
sir.
Mandar.
Okay, so let's start the session.
Okay.
So I welcome you all once again to the
Just a minute,
orientation
sir.
course.
Sir, 1 minute. Sir, just a minute. So good afternoon to all. I welcome for the today's keynote speaker, Mr. Mandar Inamdar. He is going to deliver a topic on 3D experience FEM, that is Simulia. Now I would like to hand over the session to Mr. Mandar Inamdar. Okay, sir. Now you can start, sir.
Yeah, thank you once again.
Thank you,
So,
sir.
yeah, let's begin the session. So I was informed that students who are joining are from sixth semester, is it? So is everyone from sixth semester, or
Yes, sir.
there are
Yes,
some
sir.
seniors too?
All are from sixth semester, different. All are from sixth semester
Branches.
student, different branches.
All right.
EC Mechanical,
So,
IS, and CS.
all right. All right. So yeah, so when I learned actually FEM, so it was there in sixth semester itself. So assuming that you all are beginners or freshers to the concept, so we will start today's session with a brief introduction and then see different stages and like things will follow as per the slides which we have. So if you can see this picture, everyone, uh, this is the landing gear, okay? And the part which is highlighted is what is being analyzed actually with the help of finite element analysis. And this part, the results of this part is shown, okay? So this is the landing gear, and out of the assembly, so only this particular strut is being analyzed, and here we can see the stresses, okay? So whenever we perform an analysis, whenever we perform a simulation, okay, we can see the results in form of a band, okay, color bands. So color bands will start from blue, okay. It is a WebQR pattern basically. So it will start from blue and it will go up to red color, okay. So wherever are the red colors or relative zones, like you can say maybe orange or yellow, okay, and further down. So that is how the any field will vary, okay. Field in the sense the result will vary. Now the results of this may be displacement stresses or anything else, okay. So but displacement stresses are the one of the basic things which we get out of a film, okay, or AP analysis. So wherever you find the darker spots, okay, dark in the sense I mean to say yellow or orange or maybe red color. So there it indicates that the value is high, basically. So wherever it is in blue in color, there is where the value will be low, okay. So I mean to say the magnitude wise, magnitude in sense number wise, right? So if you see this landing gear and think of loads which act upon landing gear, we can think of several loads. Okay. So first, as the aircraft moves along the runway, we can get we can say the taxiing loads. Okay. Then when it flies, we have maneuver loads. I mean to say while retraction and extension of landing gear, we'll get the maneuver loads. Okay. And then once it lands, we will get shock loads and impact loads. Okay. So these are few of the loads which are there while it is moving. Okay. Apart from this, we also get the loads due to the weight of the aircraft, the weight of the wing structure, and like several things. Okay. So all these things will make this particular component very critical. Okay. And we don't want this to fail in any condition. Okay. And even if there is a failure, we expect that the loads which are coming from the say ground in this particular case, okay, should not affect the inside passengers, else it will be a disaster, right? So all these things are a basic engineering fundamentals which go into a landing gear, or engineering or physics principles, I can call this. Okay. So we don't want this to fail, and even if there is a fail, like in case of heavy landing, we don't want the what we can say the deformation of landing gear to not affect the basically structure. First of all, we don't want even the structure to fail, okay, and then also the passengers to fail. So all these things will make the component very much critical, okay. In any case, any landing gear if you take, it will be very critical component, right? So this means what? We need to have some phase in between design and manufacture. Okay, that is a testing phase, right? So in between your design and manufacture, there is this phase called testing, right? So now testing is divided into two parts. Okay, so first comes your virtual testing. Okay, virtual testing is done with the help of computers and various tools are there in this vertical testing. Okay, various softwares are there involved, and these softwares have evolved since a long time. You can say 70 years. Okay, we're considering this year. Since 70 years, these have been there, and they have taken engineering to a different level. Okay, and they have reduced the number of prototypes. I mean to say, I'll go to that concept, and by reducing prototypes, they have reduced the costs too while the design cycle is happening. Okay, so we have the testing phase, and testing phase is divided into two parts, that is physical and virtual testing. Okay, and virtual testing is done with the help of softwares. Coming to the other part, that is physical testing or the main testing, that is done physically once a prototype is manufactured. So prototype is nothing but in the product development cycle. So once we have a design in our hands, okay, we manufacture a first prototype. Okay, directly nothing will go for production. First, a prototype is manufactured, tested, right? So once the testing components are as per our requirement, okay, once the testing is successful, then only it is taken further to the full-fledged manufacture, and then we can see the parts moving in the industries. Well, so until then, I mean to say in mass production level, until then, nothing is there up to mass production level. Okay, so this is the brief introduction of this concept. And in all this, the FEM, that is finite element analysis, is one of the concepts which will help us, okay, in this particular phase of design, that is the testing phase of design, right? So with this introduction, let us see what are the contents for today's topic. So first we will see what is the product lifecycle management. This has been done earlier also, but we will see where the simulation part will stand and how it will affect the cycle. And then we can see how an engineering problem is solved. I mean to say that there are 3 methods in solving, and we will discuss about each method. Then we will see what is the introduction of FE analysis, okay, definition of the analysis. Then we will see how it is conducted, how to conduct any FEM simulation, what are the stages, then followed by steps in FEM simulation. Okay, then once these topics are covered, we'll move on to what is the difference, like how the FEM analysis has been impacted on product lifecycle management, okay, and how it has given an impact on if development cycle is being shown. Then we'll see what are the takeaways at COE. Okay, then we will see the software part. The initial part is the theoretical part, then we move on to software. Okay, so at our center, we are using Simula Abacus and 3D Experience platform. 3D Experience platform is majorly used, but also we have Simula Abacus. If anybody is interested in that particular software, we can also handle trainings in that. So these are the different tools from Dassault Systems, so which we are utilizing in our trainings. Okay. So coming to PLM, product lifecycle management. So as we know that PLM is a process of managing the entire lifecycle of product from conception to engineering design and manufacture to service and disposal. Okay, so this particular cycle, I hope my colleague Nikki has shown you yesterday itself. So I hope you remember the different steps which are involved in any FEM process or in a PLM process. So now if you see where the simulation stands is right after design. So once we have our design, it is being simulation. Simulation is carried out, and then only we go further, as I told you earlier. Okay. So now, once the design is done, in simulation phase, we carry out the virtual testing. Okay. And then we start the process of tooling, manufacture, assembly, and things will follow. Okay. But now the inputs of the simulation are not only from design side, but it will also come from the support side. I mean to say what? So once like by chance, if any part, okay, if any part has completed the cycle process, it has gone to the support. I mean to say the production level, and then it reaches out the customers. Okay, once by their usage, if they find any default or any faults in their product, okay, they will report to the main dealer. Okay, that dealer is nothing but a company. I mean to say he is the in charge for the company at that particular place, right? So he will report the same defect to the company itself. Okay, and company will check if that is a manufacturing defect or where the defect is coming from. Is it a design defect or manufacturing defect? So they need to also reverse engineer with that defect, right? So once they find out if that is a defect in design itself, they need to improve the design, right? Improve the design in the sense what? Either they need to modify the design, or they need to see a similar kind of defect in their simulation results, right? So once if they are seeing the defect in simulation result, then they can go for improving the design. And once the design is improved, then again they will have a testing. Okay. Once the testing is complete, then they will go for production, as we discussed earlier. All right. So inputs of the simulation are coming from both design as well as from support side, right? So next we'll see how to solve an engineering problem. Okay. Consider any engineering problem. So we have these three methods which are being employed. Okay. So starting with the analytical method, then we have numerical approach, then we have experimental approach. Okay. Yes, any difficulty? Anybody is having any difficulty? Please let me know if you have any difficulty. I'll continue now. Okay. So we have these three approaches: first, analytical method, numerical method, and experimental method. Okay. We will discuss this step by step. Okay. Starting from analytical. So analytical is a classical approach. Okay. And it is suitable for simple problems, and they are solving these problems with help of formulae. And with this formula, they are getting accurate results. Okay. So now what happens is here we have examples like cantilever beam or a simply supported beam, etc. Now, like we have empirical formula for stresses, we have for displacements. Okay. This is a mechanical related concept, but to explain, I'll explain you very briefly. So displacement can be given by PL by AE, stress is given by force by area. So all this formulae hold good in analytical method. And yeah, because the area should remain uniform throughout the section, and then this will give us the accurate results. Okay, because we are solving with help of the formula. Okay, but the limitation of this is we are using analytical method only for simple problems. For complex problems where we have load coming from different points at different location, variable cross-sectional area change. Okay, so like in case of the landing gear which we saw earlier, area is not constant, area is going on changing, right? With help of any like for say x equal to 2 mm, there is a one cross-sectional area. X equal to 10 mm, there is a different cross-sectional area. Like that, the area is going on changing, right? So in this case, the analytical method will not hold good. Your standard formula for PL, force equal to or stress equal to force by area will not hold good. So here we need to have another approach. Okay, we will discuss now the experimental method. Then we will come to this procedures. Okay, in experimental method, what we do is we have real-time measurements. Okay, real-time measurements are done with help of your strain gauges. Okay, or with help of your accelerometers. Okay, like we have instruments for that. Okay, and because it is done with help of these devices, we need to have a physical prototype. Okay, means what here we should manufacture the exact product. Okay, then test it basically. So because it is requiring a physical prototype, it is again time consuming because we need to have a manufacturing for that, right? And if there are any errors in manufacturing, we need to again do it. Okay, and because it is time consuming and it will be expensive because we need to invest in a physical prototype. Okay, and because of this, what happens is in this particular method, results are finalized after multiple such testings are performed. Means what? For any particular manufacturer or of a prototype, if the testing goes wrong, okay, then we need to have a redesign. Then again manufacture the redesign and then test it. Okay, and after this, like we do this several times. Okay, and then we come on to one particular design, or we arrive at particular design basically. Okay, so results are analyzed after multiple such testings. Okay, so here we can take examples of the crash test. So all these testings, I hope people have read about this or they might have seen in some advertisements. Nowadays it is coming on advertisements too, or else you might have seen on Natural Geographic or Discovery channels. Okay, we have vehicle testings for crash. Okay, in crash we will have front impact, side impact, pole impact, pedestrian impact, how the airbag inflates. So all these are several testings. I'm taking example for a car. Okay, so all these are few of the testings which are being done on your product. I would say car is a complete product. Okay, consider that as a complete product. Okay, and these are several testings which we do. Okay, and based on all this, we give the certification. Means what? The safety standards. From here, the safety standards are set. Okay, and we need to match this before we actually go for mass production. All right, else it will be a big problem. Okay, And this is about the car. Coming to the aircraft side, we have testings like flight cutter. Okay, then we have internal tests. I'm just mentioning these two. We have a landing gear drop. We have several tests, maybe at the assembly level, at sub-assembly level, at a component level. We have lot many tests which are going on experimentally. Okay, and all with this will give it will have an investment in time as well as money. Okay, and we should try to minimize this as much as possible. And how this is done is with the help of a numerical method. Okay, now in numerical method, what we can do is we can take advantage of both analytical as well as experimental method. Okay, into the numerical concepts. Okay, how this is done. Okay, so here we need to we can replicate the real-time problems and into a virtual product form. Means what? We can replicate the real-time problems. Remember the landing gear you just saw? We can replicate that particular problem into virtual product forms. Means what? Virtual computers, we can replicate the real-time conditions. Okay, we can take any component. Okay, then we can see where it particular component has been fixed or it has been held, where the forces are acting upon. So all these conditions can be given to the problem, and then we can see a simulation. Means what? Simulation is nothing but a behavior of any product in its real time when it is being utilized, right? In its real time action, how the behavior is happening. That is nothing but called as simulation. Okay, so like take an example of say a cantilever beam. It is acted upon by a 500 Newton load. Okay, how that behaves, how that particular object behaves. Okay, when it is acted upon, that is nothing but your simulation. Okay, and how it is achieved is with the help of proper mathematical solutions. Okay, the software will have its inbuilt mathematical solution to for calculation of parameters. Parameter means what? For the case of cantilever beam, I can take parameters like displacement. I can take parameters like stresses, strains. All these are some of the parameters we can think of, right? So now in this particular methods, we have these many types again. Okay, so these are few types. This you might not grasp immediately, but once you start exploring about FEM, then you will get a fine touch of this. These are nothing but different domains in your engineering problem. Okay, I need to say the CAE or computer-aided engineering. So in this we have a finite element method. Okay, which we are discussing today. Then we have boundary element method. We have finite volume method and finite difference method. So it will have its own applications, and these are some of the problem types which you see in engineering. Okay, all these problem types are being utilized in the industries, and they are governed by these methods. Okay, these are the few of the methods. Okay, FEM for static dynamic nonlinear, boundary element for NVH acoustics, FVM for CFD electromagnetics, and FDM for thermal or flow analysis. Okay, based on these methods, the virtual software is built. Okay, inside a governing equation solving is by help of these particular methods, right? So next we will see what is FEM or FE analysis. So now there should be no confusion between FEM and FEA, right? So FEM is mostly used in universities, and FEA is practiced in industries. Okay, so let us see what is the definition. So we can break down this particular definition into 4 statements. So for a simple understanding. Okay, so now FEA or finite element analysis is a computerized method, as I told earlier, for predicting how a product reacts to real world forces, vibration, heat, fluid flow, and other physical defects. Okay, or effects, sorry. Now FEA will show us whether a product will break, wear out, or work the way it was designed. And in product development process, it is used to predict what might happen when the product is used. So it will tell us whether the product will break or it will wear out or it will work as the way it was designed. Okay, and it is used to predict what might happen. Means what? These are the conditions, right? So it will tell us what might happen when a product, any product is reused. Okay, now how does this work? It will work by breaking down a real-time object into large number of finite elements and nodes. So you can see that here we have lot of elements. Okay, so these are your elements. Okay, here we can see a 1D element. 1D means what? We'll have only one dimension. Okay, so it's not one dimension, it is all the objects will have 3 dimensions, but it is the FEA idealization of any problem which is given. Okay, this is how a 1D element will look like. This is how a 2D or a planar element will look like, and this is how a 3D element will look like. Okay, so you can see that each of the vertices, okay, over here, this is the lines, right? And the vertex will be called as node. Okay, and the line joining these two nodes will be called an element. Okay, in 2D scenario, what will happen is we will have 4 nodes for a quadrilateral or a quad element. We'll have 4 nodes, and the area which is enclosed over here will form one element. Okay, similarly in case of 3D, okay, we have 3 vertices. Okay, we have 3 nodes, and the area which is enclosed will be triangular or a tri element. And this will be the same for hexa and tetra elements. Okay, so all these are the some of the types of elements which we see in FEA world. Okay, so now mathematical equations will help us predict the behavior of each element. Right? So how each element will behave. So suppose if I utilize this element, how it will behave when it is acted on force. Okay, is what is shown by mathematical equations. Okay, and then the computer software program adds up the all individual behavior to predict the behavior of actual object. Means what? The software will do this for you. Okay, software will add up the individual behavior, and finally we will get a result for the whole object. That is what the meaning is. All right, let us continue further. Now, that was the definition, but how is it achieved? Okay, this is achieved with help of your FEM softwares or computer aided engineering softwares. Okay, so these softwares are utilized once your design is ready. Okay, means what? Once your design, that is CAD, is ready, then we move on to something called a CAE. Okay, and in CAE, FEA is one of the technology. Okay, like this we have CFD, we have multi-code dynamics, we have fatigue studies, we have engage studies. These are some of the domains. Okay, but how the process is there in FEM? Okay, this is how it can be broken down into different stages. Okay, and each of the stage will have again few more steps. Okay, we will see this one by one. So the stage 1 in FEM is called as pre-processing. Okay, pre-processing will start with the help of CAD input or creation. Okay, so why this creation is there? Creation is there because some of the softwares will help us also to create the CAD. Okay, in softwares like say ANSYS Workbench, in softwares like Abacus CAE, they will have we can do a CAD to some extent. Okay, like medium level CAD can be done within the software itself. Okay, or else if the CAD is very much complex, we have different software for that. Like we have CATIA, we have Pro, we have Creo. Those files can be imported. Okay, not only your CAD files, also we have neutral files which can be imported into your CAE environment. Okay, so once the import is done, we do something called a geometric repair. Okay, and then we can see geometric properties, we can see material properties, we can see meshing. Okay, assembly connections. Okay, apply loads and boundary conditions, define load steps, submission analysis. So all this will form a set of preprocessing. Okay, we will discuss this as we proceed further. But now to this, these are some of the steps which we follow. Okay, and each analysis should go by these steps. Okay, maybe like if your component is only a single component, maybe assembly connections will be not there. Okay, like this, it might vary here and there a little bit, but altogether, all these steps should be coming into your analysis. Else, it will throw out an error. Okay, means what? It will require all these steps as an input. Okay, we can't miss one of them and continue further. We can't do that. Right? So they have their own contribution. So once we start submission of analysis, what happens is the software internally will form a file. Okay, because software will not understand your graphics directly. Software will only work with help of binaries. Okay, so these input software will take and it will create something called as .inp file. Okay, .inp file is an ASCII text file which is read with the help of solver. Okay, so what is solver is utilized in the stage 2. What is solver is? Solver is basically a set of mathematical algorithms, okay, or programming algorithms, and the solver will help us to give out the results. Okay, now each of this program or algorithm will have its own characteristic mathematical equation, okay, which it will solve for giving out the results. Right, and this stage you might find it really confusing. Okay, but this is how the working is, and if you try to understand, it will be very simple. Right, so once you click on analysis, once you say analyze, it will form something called as IMP file that is read with the help of solver in the background. Okay, why background is you can't see anything of that is done by the software internally. okay, for calculations, right? It should calculate your displacement, stresses, and other things, right? So that is done in the background with the help of solver. And once the solving is completed, again, it will show out the results to you, right? So that's the reason it's there in background, okay? So in this stage, we see for completion of run, right? So now, once your run is complete, then we move on to the stage of post-processing. So wherein what we can see the animations as we saw earlier in sketches. Okay, we can get the graphs. Okay, graphs of say force, how it is varying with respect to displacement. Okay, and then you can create reports after that. So all this will form a stage of post processing. All right. I hope these things are very much clear to you. So anytime if you have any doubts, you can drop in chat box, or else you can discuss as we proceed further, or in the end of session, or else tomorrow also is fine. Okay, now we will see the stages one by one. Okay, let us start with the first stage where we do geometric repair. Okay, now I told about the CAD import, right? Okay, so CAD import for your different material files, CAD import for any software files. So once that import is done and your part is seen on the screen, okay, some parts might have some errors. Errors in the sense what? Some data loss might be there. In sense, some features might go missing, like say some surfaces are not there, or else some unwanted edges are there. Or else we have duplicate faces, we have duplicate surfaces. Okay, so all these are the regions of geometric repair where we need to go and manually stitch the CAD. Stitch the CAD means what? We need to make it uniform. There shouldn't be any gaps. Okay, gaps will cause what? It will cause a hollow, hollow structure that shouldn't be there. Okay, so everything should be enclosed, right? So that is where your geometric repair will come. Okay, so once the geometric repair is complete, we go for something called as defeaturing. So defeaturing means what? We are simplifying the CAD. See here, see how it is being defeatured, or we can say a simplified CAD version. Okay, all this will help us to achieve something called as high quality mesh. We will see this as we take up the slides, but remember that this is utilized in that. Okay, so what all can be defeatured? Defeatured means what? Removal basically. Okay, so we can remove the edge fillets. Okay, we can remove the surface. Here we have edge fillet. We can remove the surface fillets. Okay, we can remove the pinholes. Okay, we can remove this embossing kind of details. We can remove it. Okay, so wherever any feature is there, okay, like holes in the sense what? The hole should be less than 5 mm or 3 mm. That can be ignored. Okay, we can't remove something like a bolt hole. Okay, so bolt hole is a region of stress concentration. We should keep that. But the regions which are, there are certain limits, and these are usually given by your managers, or maybe by engineering judgment. Okay, usually the holes which are less than 3 mm are ignored in your CA softwares. Okay, so all this can be defeatured, and unwanted edges like this can be also removed. Okay, means what? The mesh flow will be correct. Okay, so all this will help us removal of high quality mesh. So what all things are listed was duplicates. Okay, I have surface fillets, I have edge fillets, I have pinholes. So all these things can be ignored to simplify the part. Okay, and this is done with the help of something called virtual topology options, which will help us do this. Right. So once we arrive at this stage, then we can take it further. So in further stages, we apply the material properties. So material properties are essential in defining our stiffness matrix. So here I have shown a case of a stiffness matrix for a 1D problem. So F equal to, we can say Kx. So K is your stiffness matrix and X is your displacement. Okay, this will form K matrix, and this will call your U matrix or displacement matrix. Okay. So all these properties, material properties, what it will include is nothing but it will be like Planck's modulus, Poisson's ratio, mass density for a static problem. If it is thermal problem, then we have thermal related properties. Okay, like this. For each of the analysis, we need to define material properties for that. Okay, so all this will help us doing calculations. Okay, so remember that I told about a characteristic equation. Okay, so all these are essential in solving the characteristic equation for any analysis. I can take it. Okay, so let us see. Material properties are required to model the behavior of FEM elements. Okay, these properties are used to formulate the stiffness matrix, and properties are defined based on the analysis to be done and type of results of required. Okay, and these are the values for a linear static 1D problem. Okay, so these are how the inputs will look like. Okay. So these are for your steel material. We have defined some inputs. So once we give these inputs, then we move to the stage of geometric properties. Okay. So though we need to give inputs for all three dimensions, that is the, like every part will have three dimensions. Okay. No part will be planar. Even if you say a plastic component, like even if you say a plastic bottle or your laptops which are there, so they will have their own thickness, like 3 mm, 5 mm, something will be there. No part is done with without the third dimension. Everything will have the thickness. Okay. And in FEM, what we do is to simplify things, we define it as 1D, 2D, and 3D. Okay, we just to simplify the what we can say the process of FEM, we are simplifying the things with help of these elements. Okay, but remember that even in this case, we will have the all three dimensions defined. Okay, only the way of interaction will be a little bit different. Okay, so this is about the geometric properties. Okay, here we can see like we have 1D, 2D, and 3D, and all like with help of this we can define. But now where to take this judgment of utilizing what kind of elements? Okay, where do I use 1D element? Where do I use 2D element? Where do I use 3D elements? So we'll discuss on this in next slides. Okay, starting with meshing. So what is meshing? Is the process of discretizing or dividing the design domain. Design domain means what? So once your design is given to you, okay, discretizing means what? I'm dividing that into smaller elements, right? So that is what the meshing process is. Okay, dividing the design domain into smaller elements. It's called as meshing. Okay. Now in this we can take up meshing with help of 1D elements. This we saw earlier also. So 1D elements may be 2 noded like this or a 3 noded. Okay. So we have also 2D elements. We have also 3D elements. Okay. So all these we saw. So here are some more details of this. So we can have also pentahedrons. Okay. Apart from hexahedron, we have also pentahedron. Okay. And this will be 1 unit of a 3D element. This will be 1 unit of a 2D element. This is 1 unit of a 1D element. Okay. Now coming to the order of elements, we can have, this is a first order element and this is the higher order element. Okay. Higher order elements will have one more additional node in between the any of the edges. Okay. So here we can see there is one more node over here in between. So this will become 3 noded. Similarly, in this particular cases, okay, we'll have one more extra node at each of the edges. Okay. It will help us capturing the geometry in much more detail. Okay, much more accurately. And it is those curvatures and all can be captured very much clearly, and the results can be obtained also with greater accuracy. Okay, so now we'll see where the 1D elements is used. So 1D elements in discretization process, it will look like this. So once we have meshed any, like this is a truss component, typical truss component. And once we have done our meshing process, it will look like this. It will look like lines. Okay, these nodes it will not seen, but just to your understanding, we are showing this. Okay, so here are your elements and these are the nodes. All right. So now, here we have a results for this, and where we can use this element is whenever the one dimension. Okay, here we have length dimension, which is very much large compared to the other two. Other two are the width and depth. Okay, so we have length, which is very much large compared to other two dimensions. There we can take a call up using 1D elements. Okay, so as we see over here, x, that is length, is very much large compared to y and z, and then we can utilize these elements. Okay, now comes the concept of this I section. Okay, we have defined x is 1 length, right? But where we should define these two parameters? Okay, where we should define a cross section? Okay, in any software you take, we will have this beam section. So in beam section, we can define whether it is a round section, whether it is I section, whether it is T section. Okay, along with that, we can define its own dimensions, how the dimensions are. Okay, how much is the length of this I. So all of this we can define in the cross section, and then we can assign to this particular sketch. Means what? The entire sketch will be having this particular cross section. Right. So I hope I'm clear to you guys. Okay. So now let us see where we can utilize 2D elements. Okay. Now before we utilize that, we'll need to do something. Okay. We need to have a workflow for that. Okay. So we cannot directly use 2D elements, but there is a process for that. So 2D elements will be typical. We can take examples of say sheet metal. Okay, sheet metal are found in your car interior trims, outside trims. Okay, then we can take examples of say plastics. So these are some of the examples where we can think of utilizing 2D elements. Okay, so 2D elements will have its process. So in process, what we need to do is first we have this part, then we extract something called as mid surface. So mid surface, as the name suggests, is a surface which is exactly at the middle of your part. Okay. So now this part may be like maybe the thickness of this is 5 mm. So mid surface will lie to the section of 2.5. Okay. So at 2.5 we extract a surface. Okay. Then we define our elements on this particular surface. So why this is done is we are giving half the thickness above and half the thickness below of the mid surface. Okay. So now in further process, we have defined geometric properties. There we can give the section as 2.5 mm thick or 5 mm thick in some cases. Okay. Means what software understand that, yeah, these elements are extruded to 5 mm. Okay. 2.5 mm at each sides. Okay. So in general, where we can utilize is whenever X dimension is very much less compared to Y or Z. So here we can see that the thickness parameter is relatively less, right? Compared to this length and this width, it is relatively less. Okay, this might be around your 100 mm or this might be around your 20 mm. Okay, so compared to these two dimensions, X will be very less. Okay, and there we can take a judgment of utilizing the 2D elements. Okay, so now we will see 3D elements. So before that, this is an example of 2D elements. Okay, so here we have, as I told earlier, it's a car door. Okay, car door is a typical example for your sheet metal utilization. Okay, also we have hoods, we have bonnets, we have a lot of parts we can think of. Considering an example of car, we can think of a lot of examples. Okay, so now if you can see this, it is having different colors, right? Okay, so what are these? Okay, now the car component will be not just one part. Okay, it will be several parts, like maybe around 40 parts or 20 parts, 30 parts. Okay, and all this is indicated with help of a color. Okay, for simplification, because these parts might have different thicknesses. Okay, maybe the thickness of this door maybe it little bit variation with respect to this yellow thing which we are seeing. Okay, internal. Okay, so that's the reason all the softwares will shade the any assembly. This is assembly because it is containing not many parts. Okay, it will give us with respect to colors. Okay, so this is how it will look upon the import. Okay, now what is essential over here is because it is assembly, we need to also define connections. Okay, we need to define weld connections where the spot welds are there. Okay, like this, there are a lot of connections which will be involved in this particular assembly. We have bolt connections. Okay, with help of bridges, we can define that. So all these connections are defined, and then it will form a system. Okay, system will be having several parts because we can't just give force over here and leave it. Okay, because only this will deform, whereas the other parts will just remain static. That will not take a part in your analysis. That's the reason all the parts, once they are meshed, as we see over here, they are given connections. Okay, connections like spot weld. Okay, like where it is being bolted, where the force is acting upon. So all this is being defined. Okay, so now once upon meshing, it will look something like this on the right side. Okay, so this is your example for 2D analysis, 2D meshing or shell meshing. Okay, now let us see about tetra and hexa meshing. Okay, we can see clearly that these particular part or this particular you can say part itself, okay, it will have more intricate features. Intricate features means what we have small features over here. Okay, and we can see that the cross section is varying drastically as we move from inside to the other side. Okay, here we should utilize the tetra elements because this will capture the volume at much easier compared to our hexa elements. So hexa elements will require a lot of practice. Okay, maybe practice, and also it will require that the component should be relatively simple. Okay, it shouldn't have so much intricate edges and features. Okay, so what is the CAD feature is like if this is a curvature, I call it a feature in CAE world. Okay, this is a, we can say here we can see a rib coming into picture. This is a feature of CAD. Okay, so all these are called as features. So this is helped with meshed with help of tetra elements. Okay, we can see that I noted initially at a show slide where the tetra elements were there. So here it is meshed, and we can see the mesh lines over here also. So if you can visualize that, if you can't, then I'll just show it to you. So see, these are lines. It is not just CAD. Okay. So whatever, once we discretize, right, we will get this mesh lines. Okay. So this mesh lines, yeah, like this is a planar actually. So along with this, inside will be going, and that will be your one element. Okay. So any element you can take, okay, with some depth. Okay, that will be your one element. So similarly over here also. So this is your one element. Along with the step, it will form one element. Like this, it is being discretized. Okay. So again, we have examples of the axle of your car meshed with tetra elements, and here we have hexa elements on. This is your rim of any wheel. Okay. Like this, you can see that like almost each and every part you see around is being tested. Okay, help of FEM softwares. Okay, like this is examples for your vehicle domain. You see. So apart from this, we can testing is also done in your mobile phones. Okay, so like this, we can think of lot many parts. Even if you take your example of your fan, even there the testing is done. Okay, so nothing is now passed without testing. So in the testing phase, all this software will be very much useful. Okay, so we saw meshing part now. Let us move on to boundary conditions. Okay, so what are boundary conditions? So they help us in defining where the model is fixed and how it is fixed. Means what? A model can be bolted. Okay, maybe it is welded. Okay, or maybe it is not allowed to move, or maybe it's allowed to move in only one direction with some displacement. Okay, so boundary conditions will basically help us in defining that. Okay, so now in this case we have this is one particular window in 3D experience, and this is fixed displacement. Means what? It will tell us how the motion is fixed. Okay, whether the motion is fixed in all 6 degrees of freedom. Degree of freedom means what? Any object if you can take, okay, we can move it in 6 particular directions. Okay, that is we have translational along XYZ axis, and we have rotational axis. Okay, it is Rx, Ry, and Rz. So any object we can take, we can move it along these axes, and basically boundary conditions are helping us to define this. Okay, so how it is being moved is what is being how it is moving is being told to software, or how it is fixed is being told to software. So this is the example of fixed displacement, and here we can see that we can have a transition XYZ and rotation XYZ. Okay, so once we check on this, means what? It is not allowed to move in that direction. Okay, so take example of any bolted connection. So in between assemblies, we have something. If we have a bolts, so at bolt location we don't want it to move, right? Okay, then we can check all these degrees of freedom, XYZ, RX, RZ, all 6 things we can check. Okay, and that will indicate what? That particular region is not allowed to move in any 6 degrees of freedom, basically. Okay, so not only this, we have again a lot of various conditions are there. We have we can define the symmetric conditions, like in models, like say your wheel itself, we can define the symmetric condition. Okay, symmetry means what? We can see maybe a wheel as an identical structure. Okay, because the wheel is like it is fixed from its radius, right? And the tire will have their own cross section. Okay, so once we define that, there is no need of modeling the entire wheel. We can just model 1/4, maybe 1/4 or 1/8 of the section, and then define something called symmetric conditions. Okay, so all this will internally reduce the cost of computation, basically. Okay, so we can define symmetric conditions, then we can define encast, means what? How the model is fixed. So every time I need not go on checking all these things. If I give encast conditions, automatically all these 6 degrees of freedom will be constrained. Okay, so not only the fixing, so if it is giving a displacement, if any part is moving by 5 mm at one direction, even that can be given as a condition. X equal to 5 mm means what? In X direction, it will move by 5 mm length. Okay, or movement in sense, we can define torques and other things also. So like this, we can define velocity, angular velocity, acceleration, and magnetic potential in case of your electromagnetic simulations, etc. Okay, so this is about your boundary conditions. Or in this we have restraints, and second is forces. Okay, so forces, once the part is held, it should have a force acting upon it. Okay, not only a point load which you can think of, but there are a lot of forces which you can think of in physics world. Okay, we have concentrated load. This is a dead weight kind of thing. Okay, maybe you can define forces on the edge. We can define traction, and like this we can continue with forces, hydrostatic pressure in case of tanks. Okay, we have bending moments, we have temperature loading in case of thermal analysis. Then we have gravity loading, we have centrifugal loading. So all these, whatever things we can think of in physics, right? All these loads can be defined in APM analysis. Okay, measure of all these loads can be defined, or it can be defined as a sum of two forces. Okay, in some cases, right? So once we define all these things, we have completed the stage of pre-processing until now. Okay, after this, once you click on solve, so okay, we found that IMP file. IMP file is given to the solver. Solver will solve the results for you, and then this is what is happening in background. Okay, so we can perform all these simulations. Okay, so we can perform a static. In static, we have linear, non-linear. So this will be 10 linear courses. Okay, we have process setting, we have transient dynamics. So all these are the different sort of analysis. Okay, this sort of analysis should be solved. Can be solved, and for this we require something called as load step. Okay, load step is where you can define your analysis type. Okay, and internally the software will arrive at a characteristic equation which it needs to solve analysis. Okay, this equation will be different for each of an analysis. Okay, for your linear problem, it is f equal to kx. Okay, for your dynamic, it will be mx double dot plus cx plus kx equal to f of t. So like this, it will have its own characteristic equation. So not directly that will be solved, but that is a constitutive equation. From that, the software will arrive at results. Okay, and here is where we are giving inputs. Okay, for this to solve, right from our initial stages, we are giving inputs for this itself. Okay, so once the inputs are given, then only it is able to solve us the question and then the results. Okay, coming to the post-processing part, in post-processing we can get results of say, animations, we can get animations of results of graphs, and so on. So here it is for displacement. As I told earlier, the red field will indicate where the magnitude is high. Okay, here you can zoom and see this is U magnitude. So magnitude is what it is. It is 18 over here. That is red color. Okay, like this it will vary. Okay, finally it is 0 in the blue region. Right? And this is how it will appear. Okay, this is one particular graph information. Okay, so this was the stages of FEM. Now remember that take any software in your hand, these stages will not change. I request everyone to please mute your microphones so that there will be any disturbance.
Mandar, please proceed.
Yeah. So now let us summarize the steps which you saw until now. Okay. So we talked about the part creation. We talked about part import. Okay. So once we have the import done, we define properties. In properties, we have material properties. We have geometric properties. Okay. Then we define SMT. So like in some property, as I told you. So in this case, we have this particular lug, and this is a shaft, and shaft is placed in the lug. Okay. Please mute yourselves, everyone. Then we define the load step, the analysis step, which is coming into picture. Okay. Then we define the interaction. Interaction means what? In this particular case, as I told earlier, so we need to define it as assembly, right? So here, what is happening is the shaft is allowed to move about this axis. The rotational axis is allowed to move. So here I need to define that. Else the software will not understand what is happening. Okay, because I'll be applying some force at this particular location, and then I'll be fixing this. Okay, so here I'll be defining the frictional properties. Okay, so in this stage I'll be defining that, and further what is happening is this is where I define the boundary conditions. So here we can see that this particular lug is being fixed at these ends. Okay, and at the shaft location it is allowed to move on the rotational axis. Okay, because I don't want this to move along the axis. I'm interested in results in only the rotational part. Okay, I'm not thinking of this, so I'll be fixing that. Okay, and allowing this shaft to move about the rotation axis. Okay, so once we define this, we mesh the components. Okay, we submit the job. Okay, as I told you, this is the until this we have pre-processing. Okay, and it will saw the results and then it will give us the results. So here we can see the gradation and emissions. So this is the typical FPA workflow. Right. So now let us look at a small video on similar structure validation. This will basically help your understanding, and we can see where all different domains it is being utilized and how it is utilized in this video.
Today's aerospace industry is doubly challenged. Not only must they design aircraft with compressed timelines and increased rates, but they must do so without ever sacrificing quality or safety standards. This reality makes structural validation vital throughout the entire aircraft development program. Real and simulation-based validation must be performed at different levels, from the full-scale structure to coupon level. Transferring load information between these levels is crucial for accurately validating the structural performance of the aircraft. With subsystem level structural validation on the Dassault Systèmes 3D Experience platform, aerospace manufacturers can integrate analysis and design virtually, thereby reducing physical tests, increasing certification confidence, and compressing timelines. By allowing multiple groups to work on a single source of truth simultaneously, allowing for automated model creation assemblies, ability and requirements, efficiency is greatly increased, and design full integration of design and all engineering data can be directly used in the structural model, which can then be automatically selectively updated with subsequent design iterations. This saves engineering time and enables simulation-driven design decisions, ultimately leading to improved product performance. Accurate and scalable structural mechanics allow you the capability to perform predictive simulation on your virtual aircraft, including static stress, dynamic stress, and thermal stress. High-accuracy structural analysis allows you to reduce design conservatism while increasing certification confidence. High-performance computing provides the means to virtually reduce risk for highly expensive, large-scale test campaigns. High-performance visualization provides rapid and efficient insight from massive data sets, and simulation-based analytics enables collaborative decision support. By ensuring that structural requirements are met throughout the life of the program, you are able to improve product performance while lowering costs, reducing development time, and avoiding test failures. Today's aerospace industry might be full of new and evolving challenges, but with subsystem-level structural validation on the Dassault Systèmes 3D Experience platform, you will have the tools you need to keep up the pace.
All right. So we saw the process, and now we should understand that how it is been, made a difference, how it has created a difference. Okay, I mean to say how the simulations have created a difference in your product development cycle. Okay, because it is, as I told earlier, it was the advent in 70 years or 80 years from now. Okay, so how it was done earlier is being shown initially. Okay, so initially we used to have a concept. Okay, after concept we used to have a design. Okay, so once design is ready, we need to manufacture that and then do a validation. Okay, so once the validation is complete, we used to go for production. Right, this was the cycle which is followed in early days. Okay, with the advent of simulation, what is happening is, so once we have the concept, okay, so we have design. So now design not only is your CAD model, but also a CAE model. CAE model is what we talked about just now. Okay, so now design time will be little bit larger as compared to this. So because it is adding also the simulation time. So now it is not like design time is full complete and then we can start simulation. It's not like that. So we can start parallelly. Okay. So parallel in the sense what? So we need not wait until the whole assembly is ready. Okay. But if your simulations is also done on part level, we can start ready. Okay. Also before the before you actually apply to the part, if you have any calibration of material, okay, those material calibrations you can do it before even the start of your design itself. Okay, with your simple test movements, you can start the material calibration in that particular stage. Okay, then once the parts are ready in your hands, okay, then we can start the applying simulations to the part. Okay, so once your design team reaches to assembly level, we can apply to that assembly. Like this, it will continue. Okay, maybe sub assemblies we can, then we have full assembly. Like this, it will go on continuing. Okay, so simulation is running parallel with your design. Okay, maybe like we can say like maybe 5 days or 6 days after your design. That's it. I think not more than that. Okay, so now design time is little bit greater compared to your without process without simulation. Okay, now we can see that there is a drastic reduction in validation. Why? Because we are validating the any product in initial stage itself. Okay, before we actually manufacture that or before we actually build the first prototype. Okay, we are first validating that on a virtual environment. Okay, with help of your CA tools which we discussed earlier. Right. So once we have a right validation, we go for prototyping. Okay. So in prototyping, what we do is we actually do the prototype. Okay. Or we build the prototype and then we test it, as I told earlier. So validation time is reducing with significant fewer prototypes. Okay, because we have already done the virtual validation, and then physical validation will be very much less compared to the earlier days. Okay, so here what is to do, we need to iterate. Okay, means what, if one design is failure, I need to go for a different alternative. Like this, it will go on adding to the validation stage. Okay, and production stage is as it is. Okay, because we are manufacturing some units of or say some numbers, we are manufacturing that. You can see that our production of product, okay, is arrived at a right, because have you know, time savings is being a part of your labor, because your validation, you have multiple prototypes are there, we need to manufacture each of those. Okay, like this, my cycle time is being improved. Okay, and labor overheads also reduced. Okay, so now we can see how it been done. Okay, in your industries. Okay, now let us try to understand this with the help of an example. Okay, so now we have a simple bracket. Okay, this maybe we have a motor over here which has been fixed, and this is should withstand what all forces are coming out of motor. It should withstand that. Okay, so now here if it is applied by force, okay, it is failed at one location, and if this is an engineering problem and we want to solve this, we have these several design alternatives. Okay, so maybe we can increase the thickness of this particular ribs, or we can introduce a fillet. Here the concentration will be high, stress concentration will be high, so we can introduce fillet over here, or we can introduce a rib in between as a support. Okay, or else we can change the material itself. Okay, so like this, I can think of these 4 alternatives for a particular solution. Okay, but remember that, so all the 4 alternatives we are thinking of is for a material which is not so complex, or a product which is not so complex. Okay, so now if your material is titanium, okay, it will be having its own costs. Okay, if it is steel or iron, that is, I think, fine. But if it is a material like titanium is being used, that is costly, costly than US steel and aluminum. Okay, now you can think of a design. Now this design will look like it's very simple, right? It's not much complex. But imagine a landing gear in this particular place. Okay, we need to manufacture, we need to do those machinings and everything, then get the product out. Okay, and then do a testing, right? So that's not feasible, right? So the cost involved in the industries will be a lot much higher than what we thought. Okay, so like this, for a simple problem, I have the solution. Okay, and the cycle time is how it is increasing. I just told you, right? So all this will give us it is time consuming. We have more prototypes, we have labor overhead and cost to environment, because we need to extract from the ore itself, right? And it is the indirect cost to environment itself. Okay, so now if you want to, this is how a traditional cycle used to work, and this is how a model cycle will help us solving the results. So once we have any part, okay, this is in your virtual platforms. So once we have any part, we are importing that into the CA environment, and we can see like this. Okay, so we can define properties in the options. Okay, we can define the material properties and geometric properties. Then we can mesh the component. Then we can take it further to loads and boundary conditions. So here, as we saw earlier, at one location it is being fixed. At one location it's been applied by load. So all those conditions we are giving to the model, and then we are seeing the results. Okay, so we are seeing the results. Now we know our allowables for this. Allowables means what? How much stress it can withstand. We already know that. Okay, with that we can compare the values which you see in the FEM. Okay, then we can understand it clearly, saying that this is not a right alternative. I can go to the different alternative now. So like this, I can move from one to another alternative in CAE world itself without manufacturing that. Okay, so now if this alternative is not fit for you, then we can take it further to a alternative which we saw. Like this, for different alternatives, I can change it. Okay, if you want to change the material means what? This material properties will be changing. Young's modulus and Poisson's ratio will be different for that material. Those values I can apply, directly. Then give it to the FEM software and see. Okay, and once the alternative is fine over here, means what? We have virtually validated the component. Okay, this is where the virtual validation is complete, and we can take it further to production or testing stage. Like this, what I'm doing is I'm basically minimizing the risk to the product. Okay, I'm basically minimizing the risk to my product profits and business, basically. So as we see over here, prototype after simulation and design optimization is more reliable. Hence, less prototypes and labor ourselves are there. Okay, this will give us a faster development cycle and less cost to company. Okay, so this is how the bracket can be solved with help of FEA. Right. So once we understand all this, we try to summarize, and these are few videos which will help you summarize what we have seen until now. Okay.
This video will provide you a basic understanding of stress and strain, and it will help you understand material properties like elastic modulus and Poisson's ratio. We start the discussion of stress and strain using the example of a simple spring. The left end of the spring has been fixed, so it cannot move. If we apply a force to the spring by pulling on it, the spring will stretch and displace by some amount, X. The spring from a garage door requires a lot more force to stretch than the spring from a ballpoint pen. Therefore, we say the spring from the garage door is stiffer than the spring from the pen. We plot the force versus the displacement for the pen spring. We get a straight line. The slope of this straight line is called the spring stiffness and is denoted with the letter K. Mathematically, express the relationship between the spring force and the displacement as F equals K times X. If we plot the force versus the displacement for the garage door spring, we also get a straight line. As we expected, the slope of this line is much greater than the slope of the line for the pen spring. We will now use these same concepts to understand stress, strain, and elastic modulus. Let's use another real-life example. This pencil and this cylindrical piece of soft rubber have the same cross-sectional area. We will apply a pulling force to both of them. When we pull on the rubber cylinder, we can relatively easily elongate it from 5 centimeters in length to nearly 14 centimeters. When we release it, the rubber cylinder returns to its original length. Try as we might, we are simply not able to pull the pencil hard enough to notice a change in its length. So, what is happening? Instead of a simple spring, let's consider a cylinder with cross-sectional area, A, and length, L. The left end of the cylinder is held rigid in a vise, so it cannot move. If we pull on the cylinder with a force, F, the cylinder will elongate, and the right end will displace by some amount, U. We use the Greek letter sigma to symbolize stress, and we define stress as force divided by the cross-sectional area. In a similar fashion, we use the Greek letter, epsilon, to symbolize strain. And we define strain as the amount of displacement, U, divided by the original length. Now, if we plot the stress versus strain, we again generate a straight line. The slope of this line is the elastic modulus, and is symbolized by the letter E. The elastic modulus, called the Young's modulus, and for many materials it defines the relationship between stress and strain. Starting from an initial length of 5 centimeters, we elongated the rubber cylinder by 14 centimeters. This creates a strain of 1.8. Strain is a dimensionless quantity, but it is usually expressed as inch per inch, or millimeter per millimeter. So we have done that here. The elastic modulus of the rubber is 1 megapascal, and the diameter of the rubber cylinder is 6 millimeters. Using this information, and the relationship between stress and strain, we can calculate that the stress in the rubber is 1.8 megapascals. We can also use the equation for stress to calculate the force that we applied to the cylinder. What about the pencil? We know that we applied at least 51 newtons of force to the pencil. And likely, we applied 2 or 3 times that amount. So let's assume 125 newtons of force was applied. Then, we can calculate that the stress in the pencil was 4.4 megapascals. The elastic modulus of the pencil is 7,200 megapascals. This information, along with the relationship between stress and strain, allows us to calculate the strain in the pencil. Recall that the strain in the rubber cylinder was 1.8. So, even though we applied much more load to the pencil, the strain in the pencil is much smaller than for the rubber cylinder. We can now use the definition of strain to calculate how much we were able to increase the length of the pencil. The pencil only stretched by 0.006 centimeters. This explains why we could not observe any change in length. When we pull on the rubber cylinder, it not only stretches along its length, the diameter of the cylinder also decreases. We can better observe this effect by pulling on a thin rubber sheet. We used a Sharpie marker to create a 2.5 centimeter square grid on the sheet. When we pull on this thin sheet of rubber, the squares become more and more rectangular. The phenomenon that we are observing is what is known as the Poisson effect. If we define direction 1, so that it is aligned with the direction that we are stretching the sheet, and direction 2, so that it is transverse to the direction that we are stretching the sheet, we can measure how much the squares grow or shrink in these two directions. In direction 1, the square has grown from 2.5 centimeters to 3.4 centimeters. Using the formula for strain, we can calculate the strain in direction 1 to be 0.35. In direction 2, the square has shrunk from 2.5 centimeters to 2.1 centimeters. Using the formula for strain, we can calculate the strain in direction 2 to be minus 0.16. We use the Greek letter nu to symbolize Poisson's ratio. And we define the Poisson's ratio as the strain in direction 2 divided by the strain in direction 1. For the rubber that the thin sheet was fabricated from, we calculate the Poisson ratio to be 0.46. In this video, we introduced you to the concepts of stress and strain. We introduced elastic modulus, and we explained how it relates stress and strain. You saw that starting with displacement, you can calculate strain, stress, and force. You also saw that starting with force, you can calculate stress, strain, and displacement. We introduced the phenomenon called the Poisson effect. And we defined Poisson's ratio as the strain in the transverse direction divided by the strain in the direction that we apply to displacement. You can find the elastic modulus and Poisson's ratio for specific materials in many engineering reference books. They will often look similar to this table. The properties that we will enter in 3D experience are located in these columns. If you are watching this video, then you are interested in learning about finite element analysis, FEA, and how to use it. Today, I will give you a crash course on how FEA works. First, let us define FEA. FEA is simply a method that allows us to approximate the overall result for an object by combining the effects from small volumes within the object. Engineers commonly use FEA to model complex structures and thermal systems. In this video, we will focus only on structural modeling. The finite element method, which is used by FEA, starts by dividing an object into a finite number of small volumes. Similar to the cylinder that we introduced in the basics of stress and strain video, these small volumes have a simple shape which allows us to easily calculate quantities like stress, strain, and displacement. We call the process of creating these small volumes meshing the object. Each of these small volumes is called an element. We call the points located at the corners of the elements nodes. Nodes are used to connect elements. For example, node number 1 left the top corner of element number 1, top left corner, and node number the bottom right corner of element 2 with the top right corner of element number 1. Nodes are also used to apply loads to the structure. In this case, we have applied a downward force to the nodes on the right edge of the object. Finally, nodes are used to restrict movement of the structure. In this case, the nodes on the far face of the object are restricted from moving in any direction. With the left face fixed and the load applied to the right edge of the object, the highlighted element might deform like this. We can perform calculations, similar to those that we did for the cylinder in the basics of stress and strain video. We calculate the displacements and forces for every node. We then combine the forces and displacements for all the elements to approximate the overall result. We can also use the FEA process to analyze complex shapes, like this bridge. In 3D experience, the finite element process for the bridge consists of 3 major steps. Starting with the design model, we create a simulation model. This often entails simplifying the geometry. Then we select the element type, and create a finite element mesh. 3D experience has a large library of elements to choose from. Be sure to watch the video on element selection to learn more. Next, we select the scenario that we want to simulate. We define the applied loads and the restraints for the structure, as well as a physical scenario that we wish to evaluate. For a bridge, we may want to see how much vertical load it can support at its center, or we may want to verify that it can survive an earthquake. The physical scenario will dictate the mathematical technique that we use to solve the model. After we define the scenario, we can use our computer to solve a system of mathematical equations. This may take several hours or less than a minute, and will depend on the number of nodes in the finite element mesh, and the complexity of our physical scenario. Once the solver has finished, we can view our results and evaluate the performance of the structure.
All right. So whatever things we saw until now, those videos will help us understand that in a short. Okay. So now, once you are doing any courses at the center, and if you are into simulation domain or simulation exercises, so these are few of the things which you are going to learn. This is not only for your foundation course, but is also including the advanced course. Okay. So it will start with the introduction to FEM. That is the parts which we saw today. Okay, then we take up examples on linear problems. We have dynamic problems. We have coupling problems. We have non-linear, thermal, CFD, explicit optimization, and composites. So all these are different analysis. Okay, so now to introduce what all these things are. So introduction, we saw that we saw a lot of part of this. So linear analysis is done whenever we are interested in the region, okay, below the yield point. Okay, means what? There shouldn't be any plasticity happening in your component, and your displacement should be less. Okay, so in these cases, we take up linear analysis. Okay, we do dynamic analysis when we have a time varying load. Okay, so time varying load, or else if the load is acting for only say 5 seconds. Okay, like say in your problems, like if your crash is happening. Okay, like vehicle crash is lasting in milliseconds. Okay, so all those are the dynamic problems. Okay, so now buckling analysis is done for a slender structures. Okay, so slender structures yeah, it's like you can take example of a yeah, this particular is a it's a hollow cylinder. Okay, not cylinder, it's a box. Okay, a hollow cylinder or slender structures like say your windows. Okay, or beams or your columns. So all these are the examples of your buckling analysis. So wherever we have slender structures and it is acted upon by compressive load, okay, there the buckling failure mode is happening, and their buckling analysis will help us understanding that. Nonlinear analysis is done where we are interested in plasticity regions. Okay, suppose yeah, your deformation is larger, or if your stress is larger than your yield point. Okay, there else we are doing nonlinear analysis. Okay, now capacities of FEM is not only limited to structure but also to thermal. Okay, so here we can see example of a manifold. Okay, manifold of a it's exhaust manifold basically. So exhaust manifold will carry the hot gases from your engine to the it will pass on to the silencer and related parts. Okay, so now because of the thermal loading, the and constraints over here, the stress is happening. Okay, so in this thermal analysis, we can take examples of say conduction. We can solve for convection. We can solve for radiation. That is, all three modes of heat transfer are supported. Okay, in CFD, what we can do, this is typically in flow problems, like in case of your aircraft or say car. Okay, so we need to know the drag forces which are happening when the vehicle moves. So that is one of the things which we can find out with the help of CFD analysis. Okay, exponential analysis, as I told earlier, it is for a short duration wherein there is large deformation happening. Okay, wherein the inertia is significant, and there we can do explicit analysis. Okay, optimization is one sort of procedure like nowadays we are talking about lightweighting a lot. Okay, so lightweighting in your aircrafts, lightweighting in your vehicle. Okay, that is the optimum way it should be there for each of the components. Okay, so optimization is one of the procedures where we are where it helps us to achieve this particular purpose of lightweighting. Okay, so like topology optimization will it will along the load path basically. So with that, we are reducing the material where the wherever it is not required, it is automatically being removed from your design space. So that is what the optimization is. Now composites, I need not define this. I hope you are already aware of this. Now structures is not only isotopic, but it can be also made of different lies or lamina, which we call. These lamina can be oriented in different angles, and altogether it will give us a greater strength to weight ratio compared to the isotopic structures. Okay. Also the reduction in lightweighting and other things so are being achieved with help of composites. So all these are few of the analysis which we teach you in center in different courses. So in your foundation course, basically we are dealing with linear analysis and dynamic analysis, okay, and thermal analysis if time permits. So like this we are taking up. So also if you are really keen in learning and all, we can take up customized courses for you and teach the entire exercises for you. Now this is not only including few of the analysis which are again there. We are not including fatigue and multivariate. Those are also there in the center learning. All right. So next we can see how the software works. That is how the 3D experience Simulia is supporting in these exercises in 3D simulation scenarios. I think we can take our break now. Okay. So I think we'll gather back at 3:45. 3:40 should be fine. So we'll gather back at 3:40. Okay. Then we can take up the remaining portion. Okay. Thank you. Ma'am, is it fine if we take a break now for 15 minutes?
Mandar, we can go ahead, Mandar.
We can continue, is it?
Yeah.
With a break?
Yes, yes, yes.
Fine.
Okay, sir. Shall we start the session now, sir?
Yes, we can. No problem.
Okay, sir. By that time, you can share your screen, sir.
Yeah. I thought of starting at 3:40, but no problem. No problem.
Okay, sir.
Yeah. So let us continue the discussion. So now, until now, what we saw, okay, that can be applied for that. Okay. So till now, whatever things we saw, okay, that is the general procedure, and take any tool. So that will be the working procedure for you to solve any FEA problem. Okay. The things which I'm going to see now is related with respect to 3D experience, because it is a much higher innovative software, much high-end innovative software, and there are a bit changes in this particular thing compared to other tools. Okay. So let us see that. So first we need to see what all different apps will come under 3D experience which support the FEM simulation or FEA simulation. Okay. So now, as you all know, until now, okay, 3D experience is a single platform that extends the traditional product lifecycle management, okay, by offering a single platform for managing the CAD and simulation data processes. Okay. So this permits the seamless design iteration based on simulation results. Means what? So once we arrive at any simulation result, okay, now suppose your stress is around maybe 100 MPa, okay, and you can see that if your part is failing and if you want to change the length of any of the dimension, if you want to change in the CAD, what we can do is we can just switch between the apps, okay, switch between the apps and go and update your CAD model, okay, to a higher length maybe, okay. So once that update is done, okay, you can just update the mesh according to that, and then you can get your results for the new design. Okay, that's how it is as simple as that in 3D experience. Okay, but traditionally what used to happen is, so if you find any result in any error in simulation, you need to go back to the silo software, like silos, I need to say the CATIA or ProE or any other software you maybe. Okay, there you make the changes. Okay, then that changed result which is there of design, then we again import the model, again do all the procedures which we came across till now. Okay, then replicate the results for the new design which you have in your hand, and then see the results whether it is passing or not. Okay, this was the pattern in initial days, but now with the help of 3D experience, okay, just with the switch of apps, I can do the changes which I require. Okay, then update the results as per my new design, and automatically it will solve for me. Okay, so means what? My cycle time in the virtual platform also is being cut down, or it has been drastically reduced. Okay, so this you might not find it interesting in your in your say in your college exercises or something, but suppose you're working in a big company with a tight deadlines. Okay, suppose you have some project completion in your in future days, and you are still in in what we can say in a gamble. So in those stages, 3D experience will help you a lot in saving your time in the process of designing and respective iterations in simulation. Okay, so this is very much useful. Okay. Now here we can see the results. Okay, result of this is a pump geometry, and here we had done a pre-tension analysis. Okay, here we can see the how a part is being meshed. Okay, with help of tetra elements which you saw here. Here we can see a CAD model. It's not only CAD model. We can see some loads over here. This is nothing but a pressure force which is acting upon this plate. Okay, here we can see the results. As I told earlier, the results will vary from blue to higher colors of red, orange, and other things. Okay, so here we can see because of a pre-tension load, we can see some pre-tensioning happening at this particular location. Okay, so all this thing is done in only one particular tool. Okay, means what the model tree which we'll see further is just one. Okay, it is not different model trees for different software. It's not like that. It is just one single model tree. And not only until simulation, if you do digital manufacturing, okay, from the same CAD you can take it to digital manufacturing also. So all the things, the need of understanding different softwares, their workflows, their options, okay, how to interact with different software is being reduced. Okay, all the options are being placed in the action bar which you see in bottom of any software. There is where you find different options, and you can pick the options from there itself. Okay, nowhere on the screen you'll be finding any options. Okay, and this is common to all the apps in 3D experience. Okay, that's how the reduction in learning of any software is being reduced. Okay, now coming to the apps related to simulation, here we call it as physics modeling apps. Okay, physics modeling apps will provide us the capability. Okay, FEA capabilities integrated in 3D experience platform. Okay, they offer the capability to perform advanced structural simulations and including nonlinear effects. So if you take up any advanced course, you'll be going through all the exercises of nonlinearity. What is this, and what are the other things involved in any nonlinear analysis you will be taking up. Okay, this is a wireframe simulation, and it is solved with explicit dynamic simulation. And here we can see how the crimp is formed. Okay, so these are some of the simulations which you can perform in 3D experience. This is how the GUI will look like. Okay, now coming to the apps in detail. Okay, so here the apps have been categorized. Categorized into what? We can categorize it into model, scenario, and results. Okay, so now all these apps are grouped in VR quadrant. So yesterday you saw CATIA. CATIA was there as a part of 3D quadrant. Okay, but all the simulation apps are placed in the VR quadrant. Okay, in this VR quadrant, these are the categories. Okay, or these are the categories: model, scenario, and results. Okay, it is very much similar to what we saw earlier. That is pre-processing, analysis, and post-processing. Okay, now here it is categorized into apps basically. So what is the here in modeling? Modeling app will allow me to define my material properties. Okay, structural properties of material. Okay, then I can define geometry properties. I can create connections. Okay, I can create the mesh model. Okay, then review the mesh model, check the mesh model, whether it is right or not. Okay, so all these capabilities the structural model creation, okay, will give us. Now remember that it's not only model creation, but we have also a sub app, okay, that is called as structural mesh creation. Okay, now if you can think of why it is being categorized, why it is made so complex in terms of apps and all. Okay, because of the options. So in options of say any simulation, okay, there will be hundreds of options. If you have explored any FEM software, once you open the FEM software, you'll see 100 options on your screen. Okay, and it is up to you how to utilize each of the option. All right. So, but as I told in 3D experience, it is only placed in the action bar, that is at the bottom side. Okay, but we have different pages basically, so you can toggle between pages and find out options how they are coming up. Okay, as we toggle between the pages, you can see different options coming up as per the title which is given to that particular ribbon at the bottom. Okay, so that is why it is categorized apps. So similar mesh creation will support me in meshing, that is creation of say 1D elements or 2D elements or 3D elements. Okay, then next comes the scenario. Scenario is where you choose your load step. Okay, load step may be your thermal analysis, load step may be your structural analysis, or a thermal structural or fluid mechanics. So what all things we can think of in as we saw in the different analysis, you can pick the load step. Okay, then once you pick the load step, okay, we can define the loads and respective boundary conditions. Okay, then after that we can define the output request, like say displacement, stresses, strains, etc. We can define that and then go for solving. So for all these things, we have different scenarios. So these scenarios are with respect to the physics involved in those simulations. Okay, so now in the results we have physics result explorer. So what all simulations are there? We are dealt with only one single app for post processing, that is physics result explorer, which will give me the the results of animation. It will give me the animations, then graphs. Also, it will create reports for me. Okay. Also, I can play the animations, save the animations. So all those things I can do with help of physics result explorer. So apart from all these things, I can also export the model from this particular app. Okay, then the entire model will be exported. Okay, then I can also see the text files. Okay, simulation results are not only in terms of your graphs and visualization, but also the text formats. Okay, so wherein the outputs in terms of numbers will be written for me. Okay, so all these things can be explored with help of physics results explorer. Right. So next we can see how the workflow is. So yeah, as you see over here, you define model details such as material properties or connection behaviors in structure and model creation app as earlier. Okay, then we switch between the apps. Will allow us to all for the results. Okay, and there is no switch between app, but it will also automatically, so once the solution is complete, it will automatically turn on the physics result explorer app where you can see the results. Okay, this is how any standard procedure of simulation will go like. Okay, so next we'll see what all things are there in scenario. So as I told you, it is divided in pages. So here if you can see clearly, so this is the procedure tab. Next we give the control tab. Next we have initial conditions tab, interaction tab. Like this, it will go on. This particular small blue mark is going further as you proceed to different analysis. Oh, sorry, analysis. It's options. Okay, this is how a sequencing scenario will look like. Okay, so procedure will give me different load steps. So here we can see different icons, that is different load steps which we need to follow. Okay, so we have static load step, we have dynamic load step, etc. For different analysis, we have different load step, and in procedure we can pick up any of that. Okay, in controls tab we can define controls, like if you are having a damping value, we can define that. If you have an initial mass, like suppose you are modeling the casing of any engine. Okay, the engine will have its certain mass, right? So that mass I can define it over here. Okay, in a point value I can define it. Okay, so next in initial conditions I can define the initial velocity or initial temperature, that is ambient temperature, or initial rotational velocity. All those things I can define as initial condition. In interaction, like if I have an assembly and if there is a friction, like we saw the example of shaft and lug, and if I want to define friction, I can utilize this particular options over here. With restraints, as I discussed earlier, I can either fix along all the directions, or else I can clamp at any location. Okay, so like this, I can define the restraints. In loads, I can define different forces, as we discussed earlier, like forces, pressures, okay, gravity loads. All those things can be defined in loads. And in simulate, finally, I can give it for a submission of analysis, okay, whereby the solver solves for equations and get me the results out. Okay, so like this, it is how the structure is there for scenario app. Any scenario app if you can take it to the structure. Now let us look at how we can interact with 3D experience. Okay, so 3D experience will give me something called a simulation manager basically. So simulation manager will be giving me a list of options which we have utilized until now. Okay, not only it will be giving the list. Suppose I just suppose if I see the list, because these are some different steps which are followed in simulation. Okay, now suppose if I want to change any force value, so now it is 500 Newton over here. I can double click over here. Directly it will take me to that particular window. And so directly that particular option will be open for me, and I can edit it over there. Okay, so all these ways the simulation manager is helping me. So it will give a summary of options which you have utilized until now. So all will be listed out, right? So once after that, we can see so in this particular case, I'm giving a pressure input. Okay, so pressure value is given, and here we can see 4 entities. Means what? If I click on this and then pick the 4 faces, okay, so wherever is the cyan or sky blue, suppose we have a lot of options over here, and wherever the sign is coming, right, that is where I'm giving the inputs. Okay, now for pressure application, I need to pick the surfaces initially. So here what I've done is in support, I have picked my pressure. Okay, I've picked the surfaces, that is 1, 2, 3, and 4 over here. So all these spaces I've picked and I've given a surface value over here. Okay, so this is how it will look like. Okay, so this is action bar for you. So in action bar, we have again two things to discuss. So we have something called as fixed area of action bar. So remember that whatever apps you use for simulation, this fixed will be constant. Means what? There will be no change on this particular side. Okay, that is left around 5 options will be fixed. Okay, do whatever options you jump in between this, but this will remain same. Now, this is one of the options in fixed action side of action bar. This will allow me to interact with the structural model, mesh model. Instead of going to VR quadrant, clicking, and then coming to the app, I can directly toggle from here. This is a shortcut which they have given. Okay. Now, this is how the tools will vary. Now, suppose if you come to this particular page, then the options will be different. Okay, like this, all the options are grouped in action bar. Okay. So finally, this is the analysis case and this is the steps. Okay. Now remember that analysis will not only contain only one load step. Okay. Maybe for the first load step, pressure is coming. Maybe for second, some force is coming. Like that, I can have multiple load steps. So all those load steps are, listed out. Okay. As we take up simulations, you can understand this. Okay. So now in this case, we have 3 load steps and the whichever things we select, okay, for that particular step, I can give the inputs. Okay, then again come to this particular, then we can see the radio button on this side. We can click on that and then go to the further load steps and give straight inputs. Okay, so finally last load step you should pick and give for simulation. Means what? It will solve for the like suppose if you have third load step or 3 load steps. Okay, go to the third load step, give inputs for that. And then if you click on solve, it will solve the entire 1, 2, 3 simulations. Okay, then the effective results can visualize. Okay, so these are different things you need to know. So this is what is a summary of what we have discussed until now. So as I told you, we can see also the text results. So those will be written over here. So once your simulation is complete, there is something called diagnostic viewer. So diagnostic viewer, suppose your simulation is been errored out. Over here, we can see the messages and we can infer where we have given, different or wrong inputs. So it is being written over here. Okay. Also, the message will appear that analysis succeeded over here. So in basic, if there is an error, it will give me one line, explanation of what has happened. Okay. So instead of going over here, opening the message file, opening the text and seeing, in basic only we can understand whether it has failed or passed. If it is failed, where it is failed, it will show up. And if I click on suppose it is failing, okay, and if I click on that particular name, okay, directly on the model tree on the left side, it will show for me that particular option, and I can directly go there and do the changes. Okay, so these things maybe not for now. It might not, you might not feel this is significant because this is the first time maybe you are seeing the software and maybe you are still in the learning stage. But if you are, an experienced person and you come across a lot of simulations, this will be very much helpful for you. Okay. So now after all this, we continue further. In the results tab, we can see different results over here. We can see so many plots. We can plot the maximum minimum stresses, maximum minimum speeds. Okay, internal cutouts we can visualize. That is, if we move this particular, we can say compass. Okay, like this, we can visualize what is happening inside any particular part. Okay, so all these things we can visualize. Okay, now coming to unit conventions, now what is happening is all the companies like major OEMs are spread throughout the world. Okay, so maybe like it will be, the work is not happening at only one place actually. So there will be a lot of companies, like we have tier 1 suppliers, we have tier 1, 2 suppliers. Okay, so like suppose for your company, maybe the simulation part is done by some other company, okay, and that some other company will be there in India or say Japan, somewhere else, okay, and you follow a different unit system, like suppose you are working with say inch pounds and other units you are working with inch pounds, and your vendor may be working with help of or metric system, okay, that is a system. And then what happens is your vendor might not be familiar with your particular options. But what 3D Experience can do for you is the vendor, if he has the 3D Experience platform, and then once you import the CAD into 3D Experience platform, you change units from maybe versus inch, and if he just changes the unit to mm by setting the preferences right. Okay, so he can set his own preferences and then make a workaround. Okay, so instead of changing all the dimensions by himself, he can directly go to 3D Experience platform, set the preferences as he wants, and then see the units being changed. Okay, so here we can see it is 0.833 inches. So once it reaches to mm, directly the mm results will be given. Just for one window which they have taken as example, and they have shown it for you. Okay, so now where this has been set, okay, on the top bar we see these options. So in preferences we get this under general we get this units parameter. So once we click on, it's not only for length which you are seeing, but even if a kg is, maybe they are using pounds and you are familiar with kg, okay, you can change even that. Like this, you can make a workaround. Okay, and instead of converting all the units by yourself manually, 3D Experience will do it for you. Okay, so this is how it will function. Okay, but remember that suppose like this is very much useful for your beginners. Okay, now suppose you are working with say SI Okay, this is the unit consistency you should follow. Means what, if you are working with so respective force units will be in Newton, respective stress will be there in MPa, and respective density will be there in tons per mm3. Okay, you can't cross this. Okay, you can't solve the length with and when you want the density to be in kg per meter cube, because the magnitude for this will be it's not appropriate. Okay, so once you this is the unit consistency you should follow while doing simulation. Okay, so suppose you are going with SI meters, then this is the respective units you need to follow. Like this, I have listed the 4 systems for you. So SIMM, this is the format, and the units, if it is feet, US units in feet, and US units in inch. So this is the consistency. Okay. Now what happens is the 3D Experience, though it has the capability, maybe like change the stress units from Newton per meter square to MPa, it can do it. Okay, but while giving the inputs, this is how the format should be. Okay, for an ideal simulation to happen. Okay, if there is any change here and there, your results may be affected directly. Okay, so instead of playing around, so we need to follow the one particular system of units, and we need to stick to that particular system, and then take a solution. Maybe at the end you can give the results out the way it is required for people. Okay, but while solving any simulation, this is how we need to follow it. All right. So once units are completed, we go to time measures. Now remember that 3D Experience or say Simulia, it will solve for total time step and step times for each of the simulation. Okay, so total time will be the accumulated time for the simulation, and step time is for each of the given step. Okay, like I told earlier, maybe any analysis if we take, okay, we will be having time measure. Okay, but now time is only physically meaningful if it is tangent dynamic. Okay, means what, here I'll be interested for 0.3 seconds or 0.5 seconds, then only it is having some particular meaning. But for other cases, time will be increments. Okay, means what, if I'm giving a load of say 100%, okay, maybe for 10% load, 20% load, this is what the indication of time is. Okay, so 1 second, 2 seconds. So even it is not physically meaningful, but that is the significant load increment from the initial load increment, like 10%, 20%, 30%. Be showing us. Okay, for different increments, different results will be seen. All right. Once we have completed till here, then we look into roles. So as you know, that 3D Experience will have its own roles. Okay, for performance simulations. Now the roles have been categorized in the 3 major categories. Okay, so we have the apps which are related for structural physics. So in structural physics, we have mechanical analyst role. Okay, and platform contributor. Okay, because you are not individually doing it, you need to interact with a CAD person, you need to interact with digital manufacturing person, you need to interact with your role manager who may be a sales guy. Okay, for all these things, the platform contributor is required. Okay, now mechanical analyst role will give me the simulations for all the physics which we have seen until now. Okay, so maybe it is for meshing, maybe it is for solving your linear dynamic, maybe your structural simulation, maybe thermal simulation. So all these are being solved with help of only one role. Okay, it will give access to the all labs. Suppose you are a person of fluid dynamics. Okay, we have a different roles for that. Okay, then if you are a composites person, we have different rules for that. And just by enabling and requesting Dassault systems, you can utilize those particular physics also in your simulation procedures. All right. So this is what I had for you on the presentation side. Now, if there is any doubt until now, you can make a question and we can take it up now. So else, if there is no doubt, I'll be giving the hands-on demo, okay, or the demonstration side of my presentation. I'll start now. Any questions are welcome.
Dear participants, if you are having any question, you can ask now only.
Yeah, now on, we can have it at the session itself, no problem.
Yes, you go ahead, Mandar, with your demonstration.
Yes.
Student, anybody is having any questions? At least you can put it in the chat box.
All right. So let us continue the discussion. See one of the demonstrations. Okay. And before that, we will be having the short presentation on that. And then we can take the remaining session. Just a minute.
So one more session is there, sir? No?
No. I'll be continuing the same. Okay.
Okay, sir. Okay.
Yeah. So this is a stress analysis for handicap bracket, okay, using Simulia. So if you are taking up any courses, this is one of the beginning exercises you should take up as your understanding of the course. Okay, now what is landing gear bracket and where it is utilized? Okay, this is one of the part which we can see over here in blue. This is your landing gear bracket, and we can see that it is being held with help of boards at this location. Okay, and over here we have some pipelines which are going through. Okay, basically these pipelines carry the hydraulic oil from the reservoir to your actuators. Okay, and because of that, what is happening is the pressure is being imparted at these regions. Okay, and your landing gear bracket should withstand that pressure of oil. Okay, when it is actuating, when it is retracting, so all those loads it should withstand, and then it shouldn't fail or bend over here. Okay, which was it will be a fracture in pipeline itself, and then maybe your hydraulic pipe line might be a leakage. Okay, so we are analyzing this because we need to determine how many such brackets are required. Okay, for the carrying this particular liquid from its reservoir position to the actuation position. Okay, so this is how the assembly view will look like. Now we'll see this particular part and try to test it with help of FEA, and then see different results which are going to take place. Okay, when it is being analyzed. All right. So how to how to do this procedure? Okay, we will take it up with help of slides itself. So once you open 3D Schemes platform, okay, on the right have this particular option. We need to set up the options which are in general. Okay, so this means what all options we are doing, it will be a separate geometrical set and it will not affect the CAD. That means what? Also, individual geometry set or loads with affected. Okay, so this is what the broad meaning is. So once I set the options, once I set the preferences, I can import the CAD. Okay, so import will support vast of the file format which are existing. All the files formats are supported. So in this particular case, it is .sat format, and this is how the file import is happening. So once you click on OK and import over here, this is how it will appear. Okay, and now by default it will open up in CATIA simulation model preparation or maybe assembly design or part design, but it will open in CATIA. Okay. Now, in my explanation earlier, I left one of the part, the simulation model preparation. You remember the phase of de-featuring or geometric prepare, which we discussed earlier. Okay, that is being dealt with help of simulation model preparation. Okay, and because it is related to CAD, it is grouped under CATIA. Okay, so in CATIA itself, in 3D quadrant, I'll be finding a simulation model preparation, which will help me in de-featuring duplicate surfaces, pinholes, removal of any unwanted details, simplifying CAD basically. So in all this, the CATIA simulation model preparation app will help me out. Okay. So now, so once I do the changes, so in this case, it is not there, but let's say for complex structure, yeah, I need to have something. So I'll be doing those changes and taking it further. So as we know, in now, so all the simulation apps are grouped in VR quadrant. Okay. Now what we do further is we click on VR quadrant. Okay. We go to structural model. So I hope you remember that structural model is helping me to give me the material properties, the geometric properties, the connections, and other things related. It is helping me. Okay. So here I can find it. So if you have a a quick view, so all the apps which are there in the cyan color are with help of Simulia. Okay, are with respect to Simulia. Okay, Simulia apps. Okay, so those are with yellow color are grouped under Delimia, that is digital manufacturing. This is how the software is helping me to identify the apps. We need not read everything. Okay, we can just also, if you are familiar by doing few simulation, so your hand will directly go to this particular app just by looking at the design. Okay, not even reading is required. So now if you pick the app, it will ask me what is the initialization method. Means what, I can have different methods for initialization. Means what, if I click on maybe automatic, what will happen is the part will be meshed automatically for me. Okay, I need not do the manual meshing every time. Okay, so here, since I want some control in my hands, I can pick it as none. Okay, so now there are other options like rule based or procedure based. So why these are there? So now suppose you are dealing with assembly of say 10 components. Okay, you can define something called as rule. Okay, the rule, we can just browse the rule over here, and that particular mesh size, say of 5 mm or 10 mm, it will directly come, and based on that, the entire assembly will be meshed. Okay, and need not again go on defining every time. So particular method is called as batch meshing. And batch meshing is, typically it is used in case of large assemblies, like maybe you have a full car model or a full bus model. Okay, in this cases, for your say your durability studies, or say for your enriched studies. So in all these cases, the batch meshing is helping. Okay, because the meshing is a tedious process. Okay, and there are a lot of engineers which are employed in this particular process, basically. So if you take any simulation team, okay, so if you take a team of say 20 members, out of that 10 members will be there for meshing itself. Okay, and 5 might be there for your connections, and maybe those 5 analysts will also support in analysis. Okay, and we'll be having 2-3 experts. Okay, in analysis. Okay, and finally one guy who is a team lead who is also analyst itself. Okay, but major work is the meshing work. Okay, and it is a bit time-consuming process, because we need to take up each part. We need to mesh the component. We need to assemble the component. Okay, then we need to clear for quality. Okay, and make the assembly ready for simulation. So this is one of the task-consuming process which is there. So for this, we are defining rules so that our process is being simplified. Okay, and the significant time is being saved by the team. So all those options are there. Now, as we are working with 3D experience, what is happening is the model will remain constant. Okay, so what all things are defined until part body were the part of your CATIA part design or CATIA assembly design. Okay, but once you continue further, it is the simulation options which come up. Okay, now once you click on none over here, once you enter structure and model creation, automatically first options will be nodes and elements and properties. Okay, now if you can visualize this small yellow mark will appear where my inputs are still not given. Okay, to the model. Okay, means what, I can double click over here and give the inputs. This is how the software is interacting with the user, saying that yes, you need to still define it over here, and the options for this is not there. The options for this is not defined, because what happens is at the end of the analysis, if I give an error, okay, again I need to redo it. Instead of that, this is how the software is telling me basically. Okay. All right. So once if you click on structure model. Then we need to set up, go to setup, and contributing shape we need to pick. Means what? I can pick the 3D shapes over here, okay, which are the contributing analysis. Those I can pick. Then take it further, where you can define the material properties. Okay, there is one more interesting thing about material properties. Now, Simulia or 3D experience, okay, will have a large library of materials. Okay, so those materials, once you start defining material, it will save in the background cloud. Okay, and these materials can be obtained whenever you want. Okay, no need of creating new material again. It will be there in cloud. Suppose you are creating material for today, and if you want maybe some analysis is similar and you want to retrieve that, you can directly go to the cloud and pick the material which you require. Okay, so those materials is being listed out over here. Okay, like this, what all materials you have presented now will be a list, and directly instead of again defining this, there are any edits which are required, you can do it. Else, if the material is typically same, you can just directly say apply over here and give the values if you want. Okay, so in this particular case, we are defining the modulus of elasticity, we are defining the Poisson's ratio, we are defining density. So all those parameters you can define. Take the part further for the further steps of now if you say apply over here and then click on your sketch which is there on the screen, and with a check mark, the material has been applied to the model. Okay, so instead of redefining that, so we have a cloud which will store all your materials. All right, so once all these things are defined, I can take it further for defining the geometric properties. So in geometric properties, we are defining, this is a tetra mesh, and this is a typical solid section. So we are defining it as solid. So options for cell section, options are 1D, so are lying adjacent to this. So as we discussed earlier, we can define it as a 1D or maybe 2D or 3D section as per my requirements. All right. So here automatically show me that which material has been applied. If you want to change the material for any like maybe your assembly is part of material, it is for different materials, I can still go here and change the material for any different parts which are required. So even that flexibility is there in the simulation. Okay. So here is where I mesh. So you remember that I discussed about the fixed side of action part. So now here we can see that gray is bit darker. Okay, here we are dark gray and for gray simply, and here it is white, right? So this is what the fixed side of action bar is. Okay, on the left side. Okay, means what all options you choose, right? This will remain fixed. Okay, so in this one of the option is mesh. Okay, so now we can browse between the apps. Okay, from model we can go to mesh. So if you remember, they need to switch the app, right? This is one of the switches. Okay, so from model you enter the mesh and you pick what all options you require over here and take it further. You can give the mesh size, you can select the part body and you can mesh it and then give the update, right? So update, what it will do is it will see that whether all the options are aligned correctly or not. Okay, suppose you are taking it as cell section and if you are doing a 3D mesh, it will not update. Okay, a 3D elements will require a 3D mesh, right? So only 3D geometric sections will be there, that is solid sections will be there. Okay, so to see that the compatibility is there or not. By chance, if you have misaligned that will show up an error over here, and now also we can correct that. All right. So once after meshing, your model will look like this, and then you can see what is number of elements. You can see number of nodes. Okay. Then take it further for defining analysis. So in this particular case, if you remember that here we had pipes of pressure. Okay, that is pressure pipes and the constraints which were there at the bottom. That is bolt constraints. Okay, but in FEM we need not define those bolts and all, but we can define the respective constraints over there. So constraints are nothing but called as your rigids or spiders, which we call in FEM terms. Okay, so it will allow me to give the conditions for support. Okay, in the sense what, suppose I want to constrain this particular hole. Now bolt means what? Bolt is not allowed to move, right? Bolt doesn't allow the part to move. Yeah, then that is the condition, right? So those particular conditions I can define at this particular point or this particular location over here. Okay, that in 3D experience is achieved with help of couplings. Okay, so kinematic couplings and distributed couplings. There are two couplings which we allow me to interact. Okay, with 3D experience for creating rigids. Okay, now in this case we are giving a continuous coupling, because what is happening over here is here we have loads and load should be given to the area which is there. Okay, so now instead of creating a group over there, creating group of elements, then dividing the load value for each element and doing that, that is not a that will be very time consuming for me. So instead of that, I'll be picking these particular surfaces. Okay, create a coupling. Okay, and for coupling, I'll be applying the load directly. Okay, means what? The area will be getting the load. So like this, as there are two pressure pipes, options 3 and 4 is where I create the couplings and give respective values for that. All right. So once this is given, now the time is to constrain the bolt holes. Okay, because I don't want the locations to move. Right. So now I'll be selecting this as kinematic type. Okay, kinematic type will allow me to constrain it correctly. So here I'll be picking these two holes, and then I'll be defining constraints at regions. Okay, then taking it further, giving an update over here. Okay, just to see whether my options are correct or not again. Okay. Okay, so once that update is complete, now the time is to give the loads and select the boundary conditions. Okay, so now as we told in physics, if you can say structural physics, we have these particular types. We have thermostructural, we have thermal and structural problems. So in this case, I point force or a point flow. Okay, we are taking data structural analysis. Okay, and now in select FEM, what happens is now if you when you start doing FEA, okay, and as you gain experience along, okay, maybe you want your sizes of mesh to be like maybe from going from say 5 mm to 3 mm to 2 mm and so on. Okay, so now in other software, what is to happen is so you need to do analysis for one case, that is 5 mm. Okay, then redo the changes for 3 mm and again follow the procedure. Like this process is again iterative and time consuming. But in 3D experience, I can make such FEM models for different sizes. Okay, and just by picking over here, okay, this may be for 5 mm. Okay, next maybe for 3 mm, again 2 mm. Like this, I can pick between these models. Okay, and do analysis for that. Okay, there is again time consumption, time saving, sorry, in case of doing analysis. Okay, like this I can pick the FEM models which are there for different sizes. Okay, this is not with respect to this size, but if there is an internal change, like suppose in one case the surfaces are tied together, in other surfaces in other analysis maybe it is a friction model. Okay, like this, what all conditions are there, I can pick over here and then take it further for analysis. Okay, so here I can pick the respective FEM model. So once this is picked, it will show me a green tick mark. Again, the software is talking to me saying that, yeah, you have selected a FEM model. Now you can take up further for procedures. Now remember that it had its own flow, and the flow will be very familiar as you take up exercises, right? So now once the structure model is picked, then you can options for selecting procedure will be turned on. Okay, now you can go over here, pick the static step and take it further to analysis. So once if you select static step, then these two will be green again. Okay, then I can create loads. So I know that these are the bolt locations and shouldn't move. So I'll be fixing all the degrees of freedom and these regions. Okay, so here and here, both the ways, it is fixed in all directions. So this option you also saw in earlier slides. So now we are seeing the application of that basically. So like this, both the bolt locations are fixed where it has been held. Okay, these loads we have calculated, and as the pressure load is in this transverse direction, we are applying the load in this particular direction, that is in Z direction. Okay, so once the load has been applied, it will look something like this over here. So arrow is pointing over here. Right. So now we can take it further to analysis. So here basically I can select the number of ports which are required. Okay, I can select the number of spheres which are required. Okay, so now I can take it further for solver run and see the displacements. Okay, and see that stress results which are happening. Okay, now we can see the mesh lines. Okay, and the results are automatically probed. Means what? If you just move the cursor along the model, you can see the results which are coming up. Right. So if we change the plot, so here, this is a plot browser basically. Results of different steps are lined over here. Okay, so here in this case we have only one step, and in plots we can select different plots like say displacement. Okay, Then this is for one particular test of strength, and we are using AL707 material, which is having 503 PA of allowables. Okay, and my stress values are very much below this, and we can see that this part is safe under the loading, basically. So this is what I had for the demonstration. Now we'll quickly see on 3D experience one particular model, which we just spoke about. Okay, so we will discuss options one by one. So once you import the model, as I said here, so until here is your CAD. Okay, from here your simulation process begins. Okay, so the first stage is where you mesh the component. Okay, so if you click on this, mesh creation will open up. Okay, so here is where I can define my mesh size and whether it is yes, sir.
Yeah, we are not
Yes,
able
sir.
to see anything on the screen.
Okay, just a minute, sir. I'll reshare the screen. Sir, now?
Okay.
Okay. So just to repeat few things. So until here was your CAD model, basically. So just double click on part body, the part will appear in CATIA. So below this, the model tree will be continued in simulation. Okay. So this is how the part will be meshed like, and this is how the mesh will look like for you. Okay. So this is a tetra mesh. Okay. So this is how it will appear. So if you double click on this, yeah, this is the where you give the sizes for the mesh. Okay, here you can select whether the part is maybe a linear linear order or a higher order element. Okay, so then once this is set, we can see the here is where a switch is. Okay, so here once we give the switch, so remember that what all apps we are using, the name is appearing on the top left side. Okay, or the top left corner of 3D experience. Okay, so here the app name is structural model creation. Initially it was Simulia mesh preparation. Okay, so apps will this will allow me to again choose the properties. Okay, so here the solid section is created. Okay, so this is how it will look like. Solid section, and then once this is done, coming to the material side, so we have a different app altogether. Okay, called as in VR quadrant, it will be there. Okay, so this is how the quadrant will look like for you in VR side. So structural or material definition will help you to create the materials. So this is what the, what all materials you create until now, all will be listed out over here. Okay, so now here is where you enter the material properties. Now these material properties are the characteristic of stiffness matrix which we give, and it is characteristic of type of analysis which you perform. Okay, so with respect to that, it is not required for everything to be defined. Okay, with respect to the stiffness matrix, with respect to options which you are looking for or solving for, these are defined. Okay, and in this particular case, I'll be defining density value. Okay, and elasticity value for Young's modulus. If your material is a composite, you can select isotropic. From here, you can go to lamina and do the composite properties itself. So altogether, it is being grouped in one particular app for meshing, for material definition. And again, if you create material, as I told earlier, it is stored in cloud, and you can retrieve that information whenever you want. All right. So let us continue further discussion. Okay. Now we have seen the meshing. We have seen the geometric properties. We have seen the material properties. Okay, now coming to connection side. So connection side, as I told you, so this is where the options you find in 3D experience. Okay, so connections is lying over here. Okay, so here there are a lot of options. Okay, now suppose if your part has welds, you can define welds, that is fasteners. If you can, if your part has some tie connections, tie is nothing but say like in the case of the metal joint analysis, you need interactions between two parts, right? So you need to have a load transfer between two regions, right? So there is where I can define tie contacts, and means what, the force will be transferred basically from one part to other part. Okay, and altogether it will be an assembly, and I can apply the force and see the results, right? So like this, I can have connection for spring. I can define a spring stiffness and other things. Okay. So like this, there are a lot of options over here too. So in this case, I have defined the connections for rigids. So here you can see the couplings. So couplings we can also refer on to engineering connections on the model tree. In this case, we have 4 couplings. So 1, 2, 3, 4, it will appear. So now as I proceed over here, you can see that the connections are moving. Okay, means what? It will show me where the connection is there. Okay, how the coupling is created. Okay. So next, once all these things are done, this is one part of pre-processing. Okay, then coming to scenario side. So, okay, so here we have constraints basically in the first slide. Okay, constraints is what? As I told earlier, I'll be fixing these two entities. Okay, here what I'll do is I'll pick the surfaces basically. Okay, I'll pick the connection directly over here. But while defining it as a coupling, I'll pick the surfaces and then create the coupling. Okay, so here I can fix all degrees of freedom which I want. Okay, so two entities means what? I'll be picking here and here and illustrating all DOFs directly. Okay, coming to the other side, here I'm applying loads. Just a minute. So if I go to loads over here, so this is how the load will look like in one particular direction. Okay, so if we have any load, you can pick it over here. So yeah, so once all these things are set, I can define the load step. Okay, so here it is static step. So it is listed over here in procedure. I can pick the static step which is being utilized in current model. Okay. So now, so once all these things are done, I can go further for analysis. And before that, I want a small portion to be explained. Okay. So now, if you remember that, I was talking about now selecting number of cores. Okay. So now what happens is simulation is not only done on your computer which you see in front of you. Okay. So now, if your assembly is a complex assembly of your analysis is a nonlinear analysis like a crash analysis, okay, or maybe an explicit simulation where, as discussed in the video, it is they told that it will take several hours to complete simulation. Okay, it's not only hours. I've seen simulations in terms of days to complete. Okay, they used to leave a message on their respective screen saying that simulation is running. Please don't shut down this. Okay, so it is taking times in terms of days. So for all this, we have something called as license. Okay, basically. So first we'll start with license because we have some CS and IS tools also, and maybe here your eyes will little bit open and you see that even this is also done by us. Okay, because this is a typical IT admin job basically, and what happens is all these systems which I told an example about 20 members, okay, and those members will have their own softwares, right? But this license should be given to all of the softwares. Okay. Now remember that once you are opening any software, like say 3D Experience, also in this particular case, okay, there is something called as tokens which you're checking. Okay, so all this management is done with the help of IT administrator. Okay, so IT administrator is basically he is a computer engineer. Okay, like a CS or maybe IS engineer will be, and it will be trained on the license management tool. Okay, how much tokens, how you should monitor, how the check-in and check-out should be there for tokens, and whether is all the people are able to fetch the tokens or not. Okay, so 20 is the team I just told you, but there are several teams which are working at your premises. Okay, and all those licenses should be administered. Okay, not only license administration, but I told you saw maybe in the video which was playing, they showed an HPC for you. Okay, so now these jobs which you see on the screens. Okay, so here are the checks for me. Okay, so if in this particular case it is complete, but if you remember the slides, there it was showing tokens, right? Tokens means what? It will the solver needs to check whether the sufficient tokens are there in the license pool or not. Okay, because what shouldn't happen is, as I told earlier, all this form an ILP file and it will be queued in HPC. Okay, so once your queue is proceeding further, your job will be taken up for solution. Okay, so now after hours of queuing, if you get a result saying that for so many cores it is not available for me, then it is a time waste totally. Okay, so that's the reason the IT admin is monitoring the tokens, and he'll be continuously checking for each of the run. Yeah, if sufficient tokens available or not. He'll be monitoring that. It's not only him checking, but also he'll be interacting with the people around the analysts which are there. Okay, so like this, the IT admin is also, that is the administrative part of the license is also there, and all this process is employed currently in industries, and how the computer science and IS students are helping is in this particular field. And also the secondary, we have the regions of development. Okay, so development, like suppose if I want to automate the process, like suppose I have several parts in my hand, and there is a common process to be followed. Okay, now they write a program, right? Program in this particular case, in case of 3D experience, it will be a VB program. Okay, or in other software, it's a Python program for automation. Okay, so they will automate the process for me. They will automate the options for me, and then I'll be utilizing that for my solution process. Okay, so not only the automation part, but also development part. Now remember that I told about solvers. Okay, solvers are nothing but your Fortran programs or Fortran algorithms which are there inside. And to interact with Fortran, I need to have web, right? So that web is built with respect to C++. It is a C++ program on which you develop your web. Okay, and that is interacting with solver. Okay, and again, not only C++, we have TCL/TK also coming into picture. We have Python also coming into picture. We have Java also coming into picture, and also we have the other side of post processing. Even there, we have same programs of the same languages which have been utilized for development. All right, so I just wanted to brief about this, and finally, after all this, we'll be getting the results. Okay, so results in this case, we have one which is stress, and if you just move around the object, we'll be seeing the results for that. And this is ideal because I'm fixing at this location, and I'll be applying force, means automatically at this particular location, we'll be getting a lot of stress. Okay, there is a lot of resistance basically. Okay, and then we have displacements. Okay, just remove that. Yeah, so you can see the relative displacement, how it is happening. So this is how it will show on the software. All right, so I'm at the end of my presentation for today. So if there are any questions, I'll be happy to answer. And students can clarify their doubts with me, and or it's
Students, you have any doubts, you can please ask. Or else put it in the chat box. Any doubts?
okay, ma'am. You can let me know if any questions are there, so we can take up that
Okay, sir.
maybe tomorrow also, no problem. So tomorrow the same time session will be there at 9:50. Can log in, and session will start at 10 a.m. in the morning.
Yes, sir. 10 o'clock.
10 o'clock, and tomorrow's Ramesh sir will be taking up initial session, and then followed by Madhu and Aishwarya for the afternoon session.
Okay, sir. Thank you, sir.
Okay, so I thank all the attendees for their patient listening, and thank you once again. Yeah.
Good show, Mandar. All the best.
Thank you. Thank you, sir.
So now I would like to thank Mr. Mandar Inamdar for the wonderful session. Thank you, sir.
Thank you.
Dear participants, your kind attention that every year 21st May is observed as Anti-Terrorism Day. The objective behind the observance of this day is to wean away the youth from terrorism and the cult of violence by highlighting the suffering of common people and showing as how it is prejudicial to the national interest. To achieve the above objective, various anti-terrorism programs and drives had been organized in the past. It is proposed that anti-terrorism pledge should be taken in all the government offices, public sectors, undertakings, and other institutions. So, I request all the participants unmute your mic as well as your video and repeat my words. Please, all of you, unmute your mic. Now, please, all of you, repeat my words.